Okay, so let us start the session. I will do the revision for this week 5 only, week 5 and week 7, and Jimmy and Vishal will do the revision for week 6 and week 8. Okay. So let us begin with this week 5, and I have looked at your queries. So most of you have asked for this SPD explanation in detail and regarding this eigenvectors and eigenvalues, right? So if I'm correct, let me just look at that sheet. So we have most of you students asking for decomposition, SPD, Summation Matrix, SPD. Okay, mostly it's that contents. Okay, yeah, we'll try to cover all of those. Yeah, eigenvectors of the complex matrix too. Yeah, we'll cover that. Okay. We'll cover all. So first thing is we should be understanding what is this what is this complex number, right? So before we move on to this complex number, so anything of the form of a plus ib, right? A plus ib, where that I is an imaginary number which is equal to square root of -1, that is a complex number. Okay. So that complex number, it can be represented in the 2D form by having this real value in the x in the x-axis and the imaginary value in the y-axis. Okay, but that denotes only one single number. Okay, so the complex vector is this combination of this complex numbers. Okay, here the dimensions for this is 3. Okay, 3 dimensions. And okay, so we have this x here. Okay, so we have this x here, 3 minus 2a minus 2 plus I, and minus 4 minus 3a. Okay, this is x, and if we move on, right, this addition operation that I need not explain, I guess. Okay, so the conjugate is nothing but if you have if you have a complex number of the form a plus ib, then the conjugate of it is going to be equal to a minus ib. Okay, you just change the sign of this imaginary value, and that's going to be equals to the conjugate. So what do you denote by this conjugate of this complex vector? So for each complex number in the complex vector, you just change the sign. Okay. So suppose we have this z equals x plus y, right? It's equals to 1 plus 2y, 3 minus 4 minus 5y. So the conjugate for this z is going to be 1 minus 2y. We'll just change the sign of this plus 2 minus 3. Since it is a real number, we won't be changing it. And minus 4 minus 5y, it's going to be minus 4 plus 5. Okay, so that is a conjugate of it. I hope the conjugate part is okay. Yeah, okay. So after that, if you go for this x dot y, which is this x inner product of this of these two complex vectors. Okay, so that's going to be x bar transpose. So this xy is nothing but conjugate. Okay, the way you represent the conjugate transpose of x. Okay, and this. Okay, so the properties for this inner product is x dot y is going to be equals to the conjugate of y dot x. Okay, but if you look at that, what do you say, the length of it, right? The length of this. Suppose we have this x as this. Okay, we have x as this and y as this, right? So what we got is we got this x dot x so the x conjugate transpose y as minus 19 plus 39. Okay, if you want to find out this y dot x, Okay, y dot x, then that's going to be equals to minus 19 minus 39. Okay, minus 39. So if you look at it, since we have this minus 19 plus 39 as a value of x dot y, and for y dot x it's going to be minus 19 minus 39. The length of it is going to be same because the length is equals to this square root of 19 square plus 30 square, right? Okay, so the length is going to be same. Only thing is that x dot y is going to be conjugate of y dot x, and y dot x is going to be conjugate of x dot y. Okay, so that's the first property, and this x plus y dot with respect to z is going to be equals to x dot z plus y dot z. Okay, the remaining everything we can like derive it just by having this x by transpose y formula itself. Okay, since this x dot y is going to be x by transpose y, that's why x dot cy is going to be equal to c of this x dot y, and c x dot y is going to be c conjugate of this x dot y. Okay, and this is a question. So cx dot cy is going to be mod c of x dot y. Is it like true or false? This one.
False. Sir, what is c here, sir? This is a complex number, or what is this?
Yeah, c is complex number. C is a complex number. It's false.
Sir, complex number is non-matrix, sir.
What?
Non-matrix complex number or matrix also okay. C
is just a complex number. It's not a matrix.
Okay.
Okay, C is a complex number.
That is mod C or mod C squared?
That is so in this it is just mod C.
Okay.
As per property, it looks false because just C x dot y, not mod C.
Okay, so what is the actual value? So cx dot cy, right? What is it actually equals to? Can someone tell me?
So it will be C conjugate times C.
Yeah. So what is it? Okay, what is
Yes,
it? C
it should
conjugate
be
times
C
C.
squared.
What is it? C conjugate times C. What is that equal to?
C square.
This is, sir, I think this is
It is equal to, huh?
The length of
Yeah. It's going to be length whole square, right? So it's going to be nothing but mod c whole square of x dot y actually. Cx dot cy it's going to be equal to mod c whole square of x dot y. Okay.
So this is false, right?
Yeah, this is false. Okay. So moving ahead. So the summation matrix it is actually the similar to this symmetric matrix in like if you look at this real matrices. Okay, the Hermitian matrix is before we go on, we just define this A star as this A conjugate transpose. Okay, a matrix is said to be Hermitian matrix if A is going to be equals to A star. Okay, if A is equals to A star, then that matrix is said to be Hermitian. Okay, clear?
so here
Yeah.
A star is just complex conjugate, not transpose of conjugate.
What?
Like
No.
sir,
Complex conjugate transpose.
A star is.
Yeah, A star.
Sir, and when in the unitary matrix we consider U star U, so their U star is also complex conjugate transpose. Or it's just complex.
Yeah, complex conjugate transpose. Wherever you have it star, right, then that's going to be complex conjugate transpose.
Okay, sir. Thank you.
Sir, one more thing, sir. X dot y is equal to x Hermitian y. What does it mean, sir? Here.
Okay. So normally, what is this x dot y? X dot y is nothing but x conjugate transpose y, right? What is this x conjugate transpose? That is nothing but x star, right? So they just represented it in a different way.
Okay. Thank you.
Okay. Shall we move ahead?
So I have this question in Hermitian one. So is
Hmm.
there anything that A star signifies, or it is simply that it is a transpose of the negative? I mean conjugate transpose.
It's not just transpose of negative. It is a transpose of conjugate.
So it's like that we are going to take A conjugate and we're going to transpose it, right?
Yeah. And that should be equals to A. Okay. So we will look at it like what
Could
does
you
it
please explain
actually
with the example? Since actually I did not
Yeah.
watch the video, so it's not clear for me.
Okay.
Yeah. Thank you.
Yeah, I'll show you. Okay, so if you look at it here, right? Do you want me to explain with these examples or like some different examples?
So this example would be fine.
Okay, so we have this 2, 3 minus 3a, 3 plus 3a, 5, right? What is going to be the conjugate of it? First of all, the conjugate is going to be 2, 3 plus 3a, 3 minus 3a and 5, right? Correct? The conjugate.
Yes, sir.
Right? If you do the transpose of it, so this 3 minus 3a and 3 plus 3a, they're going to get exchange, right?
Yes, sir.
Ultimately, it's going to result in again a only.
Okay. So that's an Summation matrix.
Yeah. So
Okay.
that's an Summation matrix. So if you identify like what we have done here, so what we have done is like we just doing the conjugate of it.
Hello,
and
sir.
Yeah.
Sir, the Hermitian condition here, it should not be A star equals A.
A star equals to A. Yes. A star equals to A only. That's a condition for the Summation matrix. That's what I was trying to say, right? So now this.
Sir, how A star is equal to A star? Then what is the meaning of A star then?
A star is nothing but A conjugate transpose. Okay, that is equals to A. Then that is Summation matrix. Okay. So
Just a small query
A
that
transpose is nothing but A transpose conjugate. Okay, these both the same. Okay. So we use this. What this basically if this A transpose conjugate is equal to A, what this basically says is A J I, right? A transpose A I J, right, should be equals to A J I conjugate. Okay. So if A transpose conjugate equals to A, then that's what this means, right? Aij should be equals to Aj conjugate, correct? Is this clear? No?
Yes, sir.
Yes, sir.
Right? So for Aij to be equal to Aj, okay, let us take other scenarios. When I equals to J, Aij, sorry. So this Aij is going to be equal to Ai, right? Ai is equals to Ai conjugate, right? When this happens, when will the conjugate be equals to the actual complex number, and the imaginary number is when we don't have that so suppose we have this complex number of the form x plus iy, okay, x plus iy, a equals to x plus iy, this is a complex number, okay. When will this conjugate is going to be equals to the actual complex number? When this imaginary number is 0, right?
Y equals 0.
Right? Correct. So whenever we have I equals to j, the actual number should be real number, right? It should not have the imaginary part. Correct. So when will this happen? When we have this I equals to j, then that means that we are talking about the diagonal elements. Correct. We are talking about diagonal elements. Right. So for all the diagonal elements, it should be a real number.
Sorry,
If it is to be a Summation matrix.
hello.
Yeah.
Can you repeat this line again? Why is it real numbers on diagonal?
Okay. So we have this. So any complex number is of the form x plus iy, right? What will be the conjugate of it? Conjugate of it is going to be equal to x minus iy, correct?
X minus iy.
So for x plus iy to be equals to x minus iy, so this y value should be equal to 0, correct? Right?
Yes, sir.
So this means that aii, it should be of the form x, so which is nothing but this real value only. It should be having only the real value, it should not have the imaginary value, correct? So that is why all the diagonal elements of Summation matrix, it should have this
Real values.
it should have real values, okay? And the other thing is, if you look at it, so let's say I have this, okay, when I not equal to j, yeah, I have this aij, let's suppose aij equals to x plus iy, okay, x plus iy, and we have this aij is equals to aj conjugate, right? So which is nothing but x plus iy is equals to aj conjugate, right? Correct. So I just apply conjugate on both sides. So conjugate. This implies x plus iy conjugate is x minus iy, right? and conjugate of conjugate is going to be equal to the original complex number, so that's AJ. So basically AJ is equal to 6 minus 7. Okay, did you get what I did just now? Okay, AJ is x minus 7, and AIJ is, if AIJ is x plus 7, then AJ is going to be equal to x minus 7. Okay, so if you look at it, just want to show you the example here. Come back to this Bosman example. So if this is 3 plus 3, then this should be 3 minus 3, right? Because if this is of the form x plus 7, then this should be x minus 7 for this to be summation. Okay.
So I had this query that while we are finding out, we are checking that it's if a matrix is summation or not, we find out the transpose first and then we take the conjugate, or it's vice versa?
You do it either way, it's the same.
Okay, fine.
Okay.
So we just need to keep in mind that after doing those steps, like the conjugate and the transpose, we need to get the same matrix. If it is same, then it's an Hermitian matrix, right?
Yeah, right.
Okay, so thank you.
Okay. So if you look at it,
Hello, sir.
Yeah.
Hello. So, sir, is there any other mathematical interpretation for Hermitian matrix?
Mathematical interpretation. I just told you this, right? This one. See, anything of this AIJ should be equal to AJ conjugate. Right? AJ conjugate. So basically, if AIJ of the form x plus Iy, then AJ should be of the form x minus Iy. So let's say like I have this A12, okay? A12 is of form x plus Iy, then A21 is equals to x minus Iy. Okay. And if this I equals to j, then we won't have this imaginary part, it's going to be just x. Okay. If we have this IA, right? IA, then it doesn't have this imaginary value, it will have only this
real part.
value. Okay. Yeah. So if you are able to see this, real relation in the matrix, then that is going to be this Summation matrix. Okay. In this particular scenario, we have this A11 as 2 and A22 as 5. Okay.
5.
So those are real values. So okay. So the first part is like satisfied. The other part is if A12 is 3 minus 3A, then A21 should be 3 plus 3A. Right? They both should be conjugates. So A is a Hermitian matrix. Okay. For B, if you look at it, both the conditions are not satisfied. First thing is for
diagonal are not real.
Yeah. So the first thing is the diagonal elements are not the real numbers, and the non-diagonal elements, right? They're not having this conjugate.
Conjugate.
So if we have this 3 plus 3, here we should have 3 minus 3. Okay. Then since that is not satisfied, B is not Hermitian. And if you look at C, even though we have this 3 plus 3 and 3 minus 3, the diagonal elements are not real numbers.
Real numbers.
Yeah.
Okay, sir. Got it.
Yeah. So.
Hello.
Yeah.
Sir, I have one question regarding the length computation of complex vectors. Like in the video, it was explained that we cannot use the inner product formula, which is nothing but x transpose x for the real matrices, right?
You can use that x transpose x for real numbers, but for the complex.
Yes, x conjugate transport into x.
Yeah,
for the complex
right,
it was.
Right,
but in the example, it was one example was taken as a vector 1 and I, and it was shown that we cannot use that definition. Can you please explain that why? I didn't got that reason, because the length can be 0, right?
No.
Wait.
Then 0 vector only length can be 0.
If you're talking about what's a vector, your vector is what? 1I, right?
1 and I.
This is a vector. This is a 2D vector, right?
Yes.
So what is the conjugate for it? The conjugate for it, it's going to be
1 minus I. 1.
Say, and the transpose of it is.
And transpose is 1.
Okay, if you do this 1I. 1 minus I into this 1, right? What do you get? You get
2.
1 minus I square, which is going to be 1 plus 1, 2, right? Yeah, it's correct. Where do you get 0 here?
No, it was written. I mean, it was explained in the video that if we take the formula x transpose x,
Yeah. So if you take this formula of like x transpose x, right, so it's going to be 1
0.
I and then like 1 I, right? So it's going to be 1 plus I square, which will give you 1 minus 1 as 0.
0, yes. Then
Okay.
why, like it was mentioned that we cannot use the same definition in the complex space. Why?
Yeah, because if you multiply it this way, right, you're going to get a 0. Okay, see, if you just do this,
That's not my question. Is length can be 0, right?
Or zero vector.
Hello, sir.
no, see,
Not if
let's
you
say
draw it on the
Hello?
complex.
yeah, see, let's say like
Draw the
let's
graph,
say,
it can't
okay.
be 0.
Okay, let me just take this one dimension. Okay, I have this 1 plus I. Okay, 1 plus I, that is just single number, single complex number, and then if I just do this, if I just transpose it and then multiply it, right? So what do I get just this 1 plus I again. 1 plus I into 1 plus I, that's going to be equals to 1 plus I square, which is going to be 0, right? So this what does this give? It gives the length of this complex number, right? We are talking about one complex number here, right? So irrespective of what you have, if you have this complex number, then that's going to be this 0. Okay, but the actual case is the length of this complex number is not 0. If you look at it 1 here, and then we have I here, right? So you have it here. The distance from origin, this is 1 plus 1. Which is equal to square root of 2, right? So the double of it is the square of it is 2, correct? So the length is not actually 0, but if you're just doing this as x transpose x, then you're getting it as 0. Oh, clear what I'm talking about?
Oh yes. After looking this graphical explanation, it's clear. Because in the sense like x transpose x is giving us 0, but in actual it's not a 0 length vector, it's a length for unit 2 vector.
Yeah.
Okay.
So but for the real numbers, it doesn't matter because we don't have this I, right? So that's why we just do this x transpose x. Okay.
Okay.
Okay. So we have this this is properties of formation matrices. Okay. If the eigenvectors of two different eigenvalues, right, they are orthogonal. So by orthogonal we mean that they are like perpendicular to each other, right? And they are like perpendicular to each other. Then the inner product of those two vectors, that's going to be equal to 0. Okay.
So why are they perpendicular to each other? So why are the eigenvectors are always orthogonal in Summation matrices?
Oh, that was mentioned in the scriptures.
Like not mathematically, but like like if you visualize like why it happens.
Visualize it by
like graphically or something. Like derivation part.
Yeah, I got you. So visualizing that might not be like very straightforward to understand. Okay, but like okay, I'll just look it up and then like if there is some visual way of like translating it. Okay, then I'll let you know. Okay.
Yes, sir.
This is just like a property.
Yeah, it's a property. Okay. So to find this complex, so one person asked for this. How do you find this eigenvalues, right? Eigenvalues and eigenvectors. Okay. So for finding eigenvalues, it's easier. You just do this. Okay, let's say like we have this matrix 2 by 2. Okay. A, B, C, D, something we have. Okay. And then what do we have? We have this A minus lambda I, it should be 0, right? A minus lambda I into X, this should be 0, right? So basically, since this x is non-zero non-zero vector, so the determinant of this a minus lambda that should be 0. Okay, so we use that formula and then like you do this a minus lambda b c d minus lambda. Okay, so for the determinant of this should be equal to 0. Okay, so what you do is we just know how to find this determinant, right? Okay, you'll get this. So for this in this particular scenario, we get it as a minus lambda into d minus lambda minus cb is equal to 0. Okay, you just solve for this. You know a, b, c, d. All we don't know is we don't know lambda. It's going to be quadratic equation. You solve for it, and then you get two lambda values. Okay, at max 2 lambda values. Okay, correct. Are you getting what I'm saying? Okay, you get this. You solve for this. Okay, you solve for this, and then you get lambda. Okay, once you get the lambda, once you got the lambda, okay, what you need to do is others.
I'm so somewhere is on.
Yeah, once you get the lambda, corresponding to that lambda value, you need to find this complex eigenvector, right? So the way you do that is you do this. Okay, you just substitute that lambda value. Okay, in this particular scenario, it is the lambda value is 8. So he did this a minus lambda. So he got this minus 6, 3 minus 3.
Sir, your voice is not clear.
Is it not clear to everyone?
No.
It's echoing.
Little lagging is there, sir.
Okay. I'll try to be bit louder. Okay. So we have this. If you do this a minus lambda, right? If you do this a minus lambda, you get this. You get this matrix minus 6, 3 minus 3a, 3 plus 3a into minus 3, right? So after that, we do this row transformations. Okay, we use. Okay, we transform this we transform this matrix to this upper triangular matrices. Okay, so after this, what does this give us by transforming it? That is in the sense like if you do this R2 equals to R2 plus half of 1 plus I into R1. Okay, this gives us minus 6, 3 minus 3 is 0, 0. Okay.
Can you please repeat this step once more, please?
Okay. So what we need to do is, okay, we can solve it like, okay, what will be our main goal is we need to convert this to this to the lower triangular upper triangular matrix. We do this for solving for this equations, right? Linear equations, remember? Do you remember we do this for solving for linear equations?
Yes, sir.
Yes,
right?
yes.
So similarly, we're trying to solve this here. So we just so what we want to do is we want to make this 3 plus 3i to be 0, right? So this bottom row, sorry, this second row first element, right? That should be made as 0, right? How do you do that? So we should be transforming it such that this 3 plus 3 it should be 0, right? What we do is we do R2 equals to R2 plus half of 1 plus I into R1, right? R1 is equals to minus 6. Half of it is going to be equals to minus 3. Okay. So then this is going to be equals to this 3 plus 3i, then that's going to be equals to 0. So this R2 is 3 plus 3i, and this is going to be half of 1 plus I into 3, then that's good, minus 6, then that's going to be exactly opposite of minus 3 minus 3. So this element is going to be 0.
So how you are getting this formula, this R2 equal to R2 plus half 1 plus IR1?
Yeah, you won't get it straightforward. I just tell you.
So it's a generic formula or it's a specific?
No. That is just specific to that particular thing. Okay. Can you just tell me the matrix? Yeah. So we have this as minus 6, 3 minus 3i, 3 plus 3i, and then minus 3. Now minus 6, 3 minus 3i, 3 plus 3i, and then minus 3, right? So our goal is to convert this into lower triangular matrix, right? So
Right.
our main goal is we want to make this as 0 by doing this row transformations. Okay. So what we do is we should multiply this -6 with the number such that it's going to be equals to 3 plus 3. Okay. -3 into x, it should be equals to 3 plus 3a. Correct?
Yeah, correct.
Right. So how do you do this? We just multiply it by -6 x into 3 plus 3i. We just multiply it by 3 minus 3i. Okay. 3 minus 3i. So that this will become a real number. Okay. So this right hand side it will become real number. So that gives it as what? 3 square plus 3 square. Okay. Minus 6x into 3 minus 3i. What is this? 3 square plus 3 square? 18. 9 plus 9, 18, right? Correct?
Yes, sir.
Right. So what is this? So we have -6. Okay. We started from -6 into x. It should be equal to 3 plus 3a. -6 into x into 3 minus 3a. That should be equal to 2 plus 3 square. 18. No. Okay. -6x is going to be equal to 3 plus 3a, right? So this x is going to be equal to -1 by 6 into 3 plus 3. Okay. We need to do all this. Okay. -6x equals 3 plus 3a. So the x will be equals to -1 by 6 into 3 plus 3a, right? So which is nothing but minus half of what? 1 plus I.
So we need to find the value of x, right?
Huh? Yeah. We need to find the value of x, the value which we will be like multiplying.
Sir, means it is similar to the row reduction form.
Yeah. So that's what I was trying to say. No, we just do this row reduction form such that we'll get this upper triangular matrix. Okay. Such that it will be like very easier for us to solve for these values of x1, x2, x3, and so on, like whenever we have. Okay.
But in this case, it was
how the fourth element becomes 0?
See, in this particular case, luckily, when we have this, when you multiply this by half of 1 plus a, right? Luckily, it becomes 0. Okay. Like in this particular case, only it becomes 0. It's not always true that.
How? I mean, 1 by. Okay.
Okay. So see, if you multiply this -3 by 3 into 3 minus 3a, right? If you multiply that by half of 1 plus 3a, what do you get?
3 plus 3i minus 3i plus.
You get. You take that 3 outside, so this is going to be equals to 3 by 2 into 1 plus I into 1 minus I, right? 1 plus I into 1 minus I is nothing but what? 2, right?
Yes, sir.
1 plus I into 1 minus I is 2. 3 by 2 into 2 is nothing but 3. So you add 3 minus 3, then that's going to equal 0. Okay. Only in this particular scenario, this I mean.
But so in most of the cases which are there in graded assignment and all, it becomes a pain to find the eigenvectors actually, because either the matrices are very big.
Yes. So, sir, if you can give an example of 3 cross 3x matrix, because that's a pain actually.
That will be helpful.
So and there are different vectors also available. So, I mean, you may calculate and then we have to match it with the answer. See whether.
Yes, sir. The eigenvectors may come like here also. If you see, the eigenvector comes actually as 1 by 1 and 1 plus I, but finally it turns out to be 1 minus I and 2. So,
like, could you please explain how did we convert it?
If you can give, if you can solve the example of a week 5 graded assignment 6th question. That could be.
So, I have a doubt in this question.
Hello, sir. Hello, sir.
One person at a time. Okay. I just take it on. So, okay. One question at a time. Okay. I'll answer like what are the questions I heard until now. Okay.
So could you please explain like how did we get 1 minus I by 2 after we found out x1 and x2? We found that matrix over there, x1, x2. How did we convert it into 1 minus I by 2?
What 1 minus
Sir,
I?
I have a doubt in the same. Can you explain the
Like, how did
second?
we find x? Like, could you please explain the second part of this question?
You're talking about this, right?
No,
After
sir, I
this,
understood this, how to
do you
convert it
find
into the upper triangle matrix.
How do you find x1, x2?
Yes, so I understood how to find x1, x2. It's simple solving of linear equations. How do we find the final value of x?
Okay.
Yes,
okay.
sir.
I'll just explain that. Okay. So we have this minus x into 3 minus 3i, x1, x2, right? Okay. Here what we need to do is we need to assume one value. x1, x2, right? x1, x2, we need to assume one value. What we will do is we can take either x1 as 1 or like x2 as 1. Okay. We can take in this particular scenario, they assume x1 as 1. Okay. They assume x1 as 1. So when we substitute in place of x1 as 1, then we'll get the value of x2. Okay. Are you getting what I'm supposed to say?
Okay, sir.
Hello, sir.
Okay.
Sir,
and then that's one question. Okay, that's one question. Let me just continue. Okay, let me just continue. So this 1 plus I, that's not. I mean, it's not always that for lambda equals to 8 we have this 1 plus I. Okay. Anything of the form c into 1 the complex number multiplied to this vector 1 plus I. That's going to be the eigenvector 2. Okay. That's going to be the eigenvector 2. So in this particular scenario, they just multiplied 1 minus I with 1 plus I. Okay, you got it as 1 minus I 2. Okay, so we have this 1 minus I 2 is also eigenvector, and 1 plus I, that is also an eigenvector.
So like, how do we get to know that we need to multiply it with 1 minus I? I mean, it can be any random number, right? It can be 1 minus 2i.
It depends on your scenario. Okay, it depends on your scenario. Let's say like you got, so in the question they asked you to find the eigenvectors and you got it as form of like 1 plus I. Okay, and in the option that 1 plus I option is there, then you need not change it. Okay, you need not change. But let's say like you got like the option is of form 1 minus I 2. Okay, 1 minus I 2. How do you change it?
Okay, sir. So basically, C can be any complex number, right?
Yeah. That's what
we have to see from the option that what we need to multiply with.
Right. So that's what I was trying to say. There is anything of the form C into 1 plus 1 plus I, that is eigenvector of lambda equals to 8. Okay.
So here x1 equal to 1 minus
hello,
I
sir.
x2.
Hello, sir. One request from my side. Sir, one request from my side. Like, can you please complete the revision first, because like everybody has doubts. I also have so many doubts, but if you like covered all the doubts, that would not be, I think, possible, because this is a revision session, right?
Yeah.
Like, actually, I also have so many doubts, but that would not be like possible to clear all the doubts for everyone.
No, sir. Special class is for doubts only, because the revision, if you want to do, you can see videos again. So doubts also important, sir.
I also have so many doubts.
Very much similar to the question that is on the board. We're not asking any doubt that is out of this particular aspect.
Okay.
Just
so
1.5 hour is left.
What I'm going to do is
1.5 hour is left.
See, what I'm going to do is I'm going to answer few doubts which will be relevant for problem solving and all. For those which are like more of a conceptual level and like which of like if you're asking for derivation or something, we'll just skip that because we do not have much time. Okay. So I will answer some doubts and I won't answer some doubts. Okay, that will be selective and I will select those. All right, and we will cover the entire syllabus. Okay, like because we need to discuss other weeks also, so we'll just go ahead with that. Yeah, important doubts related to exam will clear. Yes. Okay. So yeah.
Here, sir, here 2x1 is equal to 1 minus I x2. How would we come up with 1 plus I? Because if I substitute x1 as 1, I would get it as 2, x2 as 2 by 1 minus I, right?
X2 as 2 by 1 minus I, yeah. But you cannot have it as like that, right? So see. Okay, yeah, what you said is correct. So X2 is I'll tell you.
Yeah, yes, sir.
It is just this, you multiply it with conjugate only, that's it. So you have this x2 as 2 by 1 minus I, right?
Yes, sir.
But you won't have any options of this form of like 2 by 1 minus a. So what you need to do is you need to multiply it with this conjugate. 1 minus a conjugate is 1 plus a, right?
So it will become 1 plus I 2.
Yeah. So 1 minus I into 1 plus a, that's going to be 2. So this gives us 1 plus I into 2 divided by 2, which gives us 1 plus I.
Okay, sir.
But why should I multiply with the conjugate, sir? I want to have the
to rationalize.
See, just to rationalize it, yeah.
Because complex number cannot be in a denominator, so that's
Like,
the basic
it's
concept.
not like it cannot be in the determinant, but we will never denote this complex number of this form, right? We'll always denote it of the form like a plus ib, right? So
Yes,
just for that particular specific form only, we just do this.
okay, clear.
If they give you the option as like 2 by 1 minus a, you can just select that only. That's why I told you in this particular scenario, you should not just go by like whatever you got, that's not the end. Okay, you look at the options, and you try to transform it. Okay, and even when you got this 1 plus I also, that's not the final option as I told. Okay, you need to look for the options. Okay, if they are the form of like 1 minus I into 2, then you need to multiply this 1 by 1 minus I. Okay?
Can we take any values like for x1 you took 1, so can we take any value for x1 and
x1 for x1? What you can do is, see, okay, the best possible scenario I'll explain. Okay, you look at the options. And based on the options, you can select x1. Okay.
Okay, sir. And similarly, either we can select x1 or x2, anyone.
See, you can select x1 or x2, anyone. But if you're going for x1, select the x1 that was mentioned in the option, and if you're going for x2, select the x2 that was mentioned in the option. Okay.
Okay.
Sir, one question.
Yeah, let's just move ahead.
Just a moment. Sir, if you equate this first one into 2, or by default you are getting this 1 by I and 2, right? x1 by x2. So why do we need this? And similarly, without doing this R2 computation itself, we can arrive.
You're talking about by default you're getting 1 plus I.
Yes. See, if you in the second.
That's not okay. If you talk like really, even that you did not get by default. You assume that x1 has 1, and then that is how you got 1 plus I, right? I can assume x1 to be something else. Then I'll get a different x. Okay, that is why all the eigenvectors, like the eigenvector corresponding to lambda equals to 8, that is of the form C into 1 by 1 plus I.
Okay, sir.
Okay, the complex number multiplied to this vector 1 plus I. Okay, that is a generalized form.
Okay.
And so that C has to be a imaginary number, or it could be any real value as well.
Any complex number. It could be any complex number. In this particular scenario, C is 1 minus I.
So it could be any complex number, not any scalar.
Yeah.
Okay.
It could be real also. It could be real.
Here x1 arbitrarily you have taken 1, right, sir?
Yeah. X1 arbitrarily I have taken as 1.
Okay.
See, that's how you do for this. Even to get the eigenvectors of the let's say real matrices also, you do it in the same way, right?
So looking at the option, you can change x1, x2 values according to our wish.
Yeah. So based on the options, you can change it. Okay.
How do we got C equal to 1 minus I?
Okay, let's just say like you got 1 plus I, and in the options they had this first complex number as 1 minus I. Okay, then how do I get it? How do I convert this 1 to 1 minus I? I just multiply this whole vector with 1 minus I.
Okay, sir, got it. Thank you.
Okay. Or else, if you do not want to take that risk now, instead of assuming x1 to be 1, you just assume it to be 1 minus I. Okay. Look at the options and then go for it. Okay. So the unitary matrix, any matrix of the form, if it satisfies the scenario of like multiplied by u, then that is equals to I. Then that's going to be the unitary matrix. Okay. The others Okay. So the properties for this is the eigenvalues, all the eigenvalues, they'll either be equals to plus or minus 1. Okay. And the other one is the eigenvectors. If like for two different eigenvalues, right, the corresponding eigenvectors they are orthogonal. That is they're like perpendicular. Okay, similar to what we have for this Hermitian. Okay, all the unitary matrices need not be Hermitian. Okay, this is like important. Even if you look at like this particular scenario, if you look at like okay, in this particular scenario, it is Hermitian, but in other cases it might not be. Okay. Okay, no, actually in this particular scenario, it's not Hermitian. If you look at it, because cos t, that is okay, but minus sin t, they are not conjugate of each other, right? Clear what I'm talking about? In this particular scenario, U is a unitary matrix, but it's not a Hermitian matrix. Okay, since sin t is not a conjugate of minus sin t. Okay.
Sir, one thing, sir. In unitary matrix, can we say that each columns are linearly independent and they are of unit length? Then they will form a unitary matrix. Can we say that?
Can you repeat? Each columns
are of unitary length and they are linearly independent to each other. So then it is a unitary matrix. Can we say that? Because whenever we were forming an unitary matrix using the eigenvectors, we were first like we were dividing it with the length, making that vector unitary, then putting those vector in a matrix. So from that I got that idea that if those two are linearly independent and unitary in length, then we can say that the matrix formed by these two or any vectors is unitary.
See the first one, the length part, I agree with you. Okay. The other part, where you said like that they're like linearly independent, right? That I don't entirely agree.
So any matrix whose columns are unitary, then we can say that it is a unitary matrix.
Huh?
Any matrix whose columns are unitary in length, unitary in length, then we can say that it is a unitary matrix.
No. See,
sir, it should be linearly independent, na?
Huh?
It should be linearly independent, na? Because the orthonormal columns, so that is linearly independent.
Okay, sir, we can discuss it later. Though we don't have to discuss it now. We have a lot.
Yeah, the orthonormal columns, but they're not linearly independent. Okay, so but look for just for this particular scenario. Okay, don't draft like your own conclusions. If it satisfies this particular case, U star U equals to I, then that is unitary matrix. Okay.
Okay.
Moving ahead.
Sir, just one doubt. So in this ortho means Q transport Q equivalent to I, and that will be equal to Q into Q transpose, right? Means order of the multiplication will not matter or not matter.
The order of Q
multiplication.
The order of multiplication, you mean like Q transpose or like Q transpose Q? That's what you're talking about?
Yes, sir.
That doesn't matter.
Okay, sir. Okay, sir.
Okay, that doesn't matter.
Here one doubt this regarding the
because if U star is if U is unitary, then U star is also unitary. Okay.
Okay, sir. Okay.
If you're doing U star U, then you're checking for the case of like U, right? If
this is
you're
written
doing U star, then you're checking for the opposite U star. So it's the same.
Okay, sir. Okay. Thank you, sir.
Here it is written U transpose instead of U star. Why it is like that?
This is for real case. This is for real case because U star is what? U star is nothing but U transpose conjugate, right? But for the real matrices, U conjugate is nothing but U, right?
Okay.
Okay.
No, there is no example of U transpose.
Huh? See, this for real matrices. Okay, but for complex matrices, you always need to worry about that conjugate part. Okay.
Okay.
The conjugate of real number is itself right, but for complex conjugate of complex number, it's not equal to itself. Okay, that's the difference.
Sir, in the unitary matrix, can we interchange Q transpose into Q means? Can we say if Q transpose Q?
Yeah. If U star equals to I, then U star also will be equals to I. Okay. Okay, moving ahead.
Okay.
Okay, you want me to make the pace fast? I try to be fast, okay, but I'm not able to do it. Okay, so we have this diagonalization of this Hermitian matrices. Okay, for any Hermitian matrix, right? We'll have this. We can do this. We can do this diagonalization. Okay, of this matrix A into U T U star. Okay, where this T will be this diagonal matrix, and the elements of the diagonal matrix, it's going to be this eigenvectors itself. Okay. Sorry, the eigenvalues. Okay, the diagonal elements of this T, it's going to be this eigenvalues. Okay, and this U okay, we'll be sharing this document. Okay, and this U the columns of this U are nothing but this unit eigenvectors. Okay, corresponding to that.
Sir, what is the difference between we have been doing diagonalization earlier? We have always done that, for we will take out we will get the eigenvalues, put them in the diagonal matrix, and then we will find the eigenvectors and we'll make this U. How is this different from what we have done earlier, and why, it's something different? How is it different from the earlier things?
How is it different from the earlier?
Yes, sir, we have already done, actually, this diagonalization in week 4 and all, where we were not talking about Hermitian, we were only talking about similar, the what was that? One theorem was there, no? Yeah. So what I just want to ask is, how is it different? We are doing the same thing, why we have started calling it Choose theorem suddenly, and we are not talking about upper triangular matrix rather than, simple diagonal.
Priyanka, I think this will applicable to the complex matrices, and what you are telling about the spectral theorem will be applicable for the real matrices, real symmetric matrices.
Okay.
Sir, can you explain this example, sir?
This one?
Yes, sir.
So basically, this is a more general form of the spectral theorem.
Yeah, you could say that. Yeah.
So what is U star?
U star. U star is a U transpose conjugate.
Okay, that is U transpose conjugate.
Yeah.
Okay.
So this is.
But if we get same eigenvalues, so for example, instead of 3, what if we get -2 and -2? How will we write U in that case?
Then we have to do SVD, no, sir?
Yes. Then we will have to do SVD.
Okay, sir.
Yeah.
Sir, when professor is explaining, I don't know if it is the same example or the other one, he uses triangular and the diagonal matrix interchangeably. So I couldn't understand, how he is doing that. I would either get a triangular matrix or a diagonal matrix as T.
Yes,
so if you do a U star AU, you will get a T, but he seems to be using it interchangeably, triangular and diagonal.
Okay, this one, how do you get it? That's the question.
When we do U star AU, at some places he's written that it, yeah. Sir.
Okay, so let's say like that's easy, right? So you multiply this with U star. Okay, U star A is going to be equal to U star U into T U star, right? But U star U is nothing but I, since U is unitary. Okay, and after that now we have U star A equals to T U star.
Okay. Sir, I understood that particular thing, but like when we finally, he's given the derivation actually, wherein he says U star AU equal to T. At one place he's written T is triangular, And then suddenly after certain steps, he says T is diagonal matrix. So I
in that case, professor told that a triangular matrix can easily be diagonalizable using some theorems.
So do you need to further diagonalize T as well? I mean, is that what he's trying to say, sir?
No, I mean, this particular scenario, I think he was just assuming that like he just got it like upper triangular matrix. From the upper triangular matrix, he just proved that all those like except for the diagonal elements, the remaining elements are like 0. That is why you get this as like T as this diagonal matrix.
So effectively, always T would be a diagonal matrix. Is that what it means, sir?
Yeah.
Okay.
Sir, but I mean, what I understood is what he was saying was, if for Schur's theorem to work, it will work for any n cross n matrix where you can upper triangularize it using this unitary matrix. Whereas in the specific case of a Hermitian matrix, you can do diagonalization.
Yeah.
So it's like, if it's Hermitian matrix, then you can diagonalize. Whereas if it's any n cross n matrix, then you can do upper triangularize it.
Okay, so that was the difference basically then.
Yeah, so I think it's a series of steps, right? So first thing is orthogonally diagonalizable matrices are for symmetric matrices, real symmetric matrices.
Yeah, actually, I lost him in between all those steps. So I mean, till some point I understood, after which I lost it. So I couldn't get it basically.
So I think the step he takes care, he kind of says this. So orthogonally diagonalizable matrix will apply to real symmetric matrices that is covered by spectral theorem.
Okay.
Then he comes into the complex world where you get the Hermitian matrix. And then as a general case, you can apply Schur's theorem for any n cross n matrix, whether it is complex or real, to upper triangularize it. And as an extension from there, he generalizes the spectral theorem to say that for any Hermitian matrix, you can diagonalize it.
Okay.
So here you are taken arbitrarily, sir. You or we did.
U is the eigenvector. Eigenvectors of it.
U is the eigenvectors. Matrix with eigenvector.
Eigenvector given in the question.
So, sir, which type of question can come from this theorem?
Because there is no question here, I'm unable to understand, sir. What is the question here?
Yes,
Example,
yes, exactly. We are just calculating the unitary.
See, the only thing is that here the question is that Hermitian matrix can be diagonalized. Okay, you can do this diagonalization for this Hermitian matrix where U will be some unitary matrix. Okay, there exists a unitary matrix such that A equals to U, T, U star. Okay, that's one.
So by this theorem, Hermitian matrix can also be diagonalizable.
Yes.
He's using this theorem just to prove spectral theorem, I think. So the one step further from here is diagonalization of Hermitian matrices. He kind of proves that it is upper triangle and the Hermitian part of it is lower triangle, but both of them have to be symmetric. Therefore, it has to be diagonal. So Schur's theorem, sir, are there going to be any questions directly from Schur's theorem, or is it going to be more Hermitian matrix diagonalization?
See, there are like any question from Schur's theorem. It won't be like long calculations and all they might be asking is like some properties of it, maybe or like the value of T or something. Okay, it won't be like too much calculated on it. Okay, they're asking parts. Okay.
Oh, okay. Thanks.
So even while calculating T, there is a process of extending one particular vector, eigenvector, to certain bases and all such steps. I don't know whether you've covered that in these slides. So while doing that also, there is a ordered basis which we pick. So how do we pick those ordered bases is also a doubt which I have.
Ordered basis for this eigenvalues you're talking about?
No, sir. When we are finding the U star, I mean, here you in this case you've found U star, but there is a, I don't know which step it is. There is one wherein we extend the one of the eigenvectors to the basis. Suppose if it is a 2x2 matrix, we extend it to 1, 0, 0, 1 like that, and apply the Gram-Smith to obtain an orthonormal basis. So there are certain steps where we do that. In the lectures, it is there.
Yeah. So
this one. Yeah. Yes, sir. Yeah, you can explain this, sir. Probably if I have any doubt, I'll come back. Thank you, sir.
Okay. So we know that x1. So for the d value, right? We need to get a vector which is like orthonormal to this 1 minus 1, correct? Orthogonal to this 1 minus 1, correct?
So here 1 minus 1 we picked it up arbitrarily, right? We could have picked the 7 minus 2 as well.
Yeah.
Yeah, right.
That's
okay.
what.
Yeah.
So basically for 1 minus to find x1, we basically put the eigenvalues and we multiply it with x1, x2 so that it becomes 0, right?
Can you repeat?
I mean, how do we find x1? How do we find x1?
This x1.
Yes, sir.
This x1 is the eigenvector for corresponding to this value, right? Lambda equals minus 2.
Yes, sir. All right.
Okay.
Understood.
Yeah. So we have this q1 as this 1 minus 1. Okay. From that we found this q2. Okay. So the one thing is that we know that q1 and q2 they should be this. Give me a second. See, we should be finding this unitary matrix, right? Where we have this one vector as this 1 minus 1. Okay, we should be finding the other vector, right? Other vector. Okay, in this place, right? So further the condition we have is we know that we know that the corresponding vectors of this orthogonal, right? The orthogonal, right? For the 1 minus 1, what vector will have will have it as like orthogonal, like when you do this.
Dot product, it should be 0. Dot product should be 0, right? To make it orthogonal.
Yeah. The dot product should be 0. We have this. We have one vector as this 1 minus 1. Okay. The dot product with the other vector xy, it should be 0. Okay. So it will basically give you that like it's actually opposite of it. It is x y multiplied with this one. Okay. So this basically gives x minus y as 0, right? Which basically gives x equals to y, right? Okay. Clear?
Yes, sir.
So that's how you get this. You get this u as 1 by square root 2 into 1 minus 1 and 1. Okay. So by doing this u star au. Okay, we did the.
But so here there is no Gram-Schmidt used or anything. We are not extending it anywhere. It's a simple process that we did here. So here we don't do the Gram-Schmidt or anything like that, no projections and all those things.
Yeah,
because sir talks about some Gram-Schmidt process to be used, and here also I think he has done in Q2.
Yeah, here if we just look at it, here we didn't do it for this Summation Matrix or the Symmetric Matrix. Okay, he just did it for this any matrix. Like remember one student was talking about this, like where if you do not have the symmetric matrix, right? Like where the matrix is not Summation, you get a super triangular matrix. You see it here, u star au for this particular a you have 5 minus 7 minus 2 minus 4 get it as minus 2 9 0 3.
Okay.
Like you got it as like upper triangle matrix.
Yes, sir.
Okay.
Can you slightly repeat, sir? What happened here? We had the first eigenvector. We normalized it and we found the orthogonal vector. Yeah. So that is how we created our u. Then after that, then what have we done? What is this Q2? From where it is coming?
This part Q2.
Yeah, what is this?
It's the Gram-Schmidt process, isn't it?
Projecting it actually.
What is this? I'm sorry.
It's the Gram-Schmidt process which they are doing.
If you took it the other way, I guess. Let's see.
Yeah, basically Q1 and Q2 are orthogonal, right? and we are finding.
Here Q1, Q2 are exactly.
We are finding
they
here.
are not orthogonal. Okay. You do not worry about this part. Okay.
Sir, I
We are
think
finding the
question is-
component of a vector Q1 along X2, right, sir? Along Q1.
Q2 comes out to be 2.5 and 2.5. So how did we make it 1 minus 1?
And 1.
It should be 1 and 1.
Yeah, see here Q2 is not exactly this part. Okay. So
there's a misprint over there.
Sir, so my understanding is that if you're going to take any n cross, if you're taking a Hermitian matrix and we are calculating the eigenvectors, then we are going to be getting orthogonally orthogonal eigenvectors. So in that case, we don't really have to go through Gram-Schmidt process because we'll directly get the orthogonal matrix itself. Whereas if it's any other n cross n matrix, that's when we are applying Schur's theorem, and therefore we'll be getting some eigenvectors and some vectors which are not orthogonal. Therefore, we have to go through the Gram-Schmidt process to create orthogonal, to get orthogonal matrices.
That part is clear. That part is clear. Okay.
So the question is, if you're going to have, given the time, will we be getting problems where we'll have to be going through Gram-Schmidt process to arrive at these?
No. So this Gram-Schmidt process, you will not be getting it the exam. Okay. So
I have the same doubt I have, sir. Like the previous speaker said, that if we just normalize both these vectors, these eigenvectors, will that not be sufficient to create U?
So you need orthogonal vectors.
No, right.
Okay.
So
okay. Right.
Yeah,
okay.
It's orthogonal. So here, if you look at it, 1 minus 1, 7 minus 2, they are not orthogonal to each other. Okay.
Got it. Right. My mistake. Yeah.
Okay. So this part, I'm not entirely sure what we are done here. Okay. But the important key part which you should be looking at is for you to be there, all the vectors, like all the vectors of it should be orthogonal. That's why when we have this 1 minus 1, we'll get the other vector as 1 1. Okay. This part I'll look it up and let you know. Okay. And then since this A is not a symmetric or the summation matrix, okay, you will get this U star A U as upper triangle matrix. Okay. This here we just talking about the same thing. Okay. Then the next important part, look at this singular value decomposition. Okay. It talks about the generalized form of this Schur's theorem. Okay. So there we talked about A as this Hermitian matrix, right? But here A need not be Hermitian matrix, and it need not even be the square matrix also. Okay. So we get this. We can diagonalize this A as Q1 sigma Q2 transpose, where this Q1 is a form M cross M matrix, okay, and which will be this eigenvectors of this A transpose, okay. Like we'll always be doing this unitary thing, okay. We'll convert each of those vectors length to 1. Yeah, someone is saying something.
Sir, for finding the singular values, do we have to do A transpose A or A transpose?
See, if you do this A transpose or A transpose A,
yes,
both are going to give you the same answer.
But I understand, but I saw a question in graded assignment. It was a 3x4 matrix. So if I do A transpose A, I am getting 4x4. If I do A transpose, I am getting 3x3. Now which one should I do?
See, if you go for the 3x3 matrix, right, it's going to be easier, and the thing is you'll get the same eigenvalues. Okay, just because singular eigenvalues, in a sense, like you should be considering the eigenvalues which are not 0, right?
Yes. Yes.
Right? Which are not zero, only those we should be considering. Even if you go for either one of it, we'll get the same answer.
Okay. Okay, sir.
Yeah. Okay.
Can
So
you just scroll up a little?
yeah.
Can you just scroll up a little?
That's it.
Not scroll down, sir. Scroll up. Right?
Uh-huh.
Sir, can you explain the spectral theorem? I was actually confused about it.
This one?
Yes,
We
spectral
talked
theorem.
about this all the while, right? See, if A is a summation matrix, then you get it. Then you have a matrix such that A equals to U D U star, where D is this diagonal matrix. Okay, but in the general case, where A is not a summation, then this D is going to be upper triangle matrix. Okay, but if this A is a summation matrix, then D is going to be the diagonal matrix. Okay.
Means it is a special case of Skur's theorem, right?
Yeah.
Okay.
It is special
Okay.
cases. Okay.
Sir, while doing the SVD, we get two different matrices Q1 and Q2. So Q2 is basically the eigenvectors of A transpose that has been normalized, right?
Right.
For Q1, I get another set of vectors which are basically Y1. I mean, sigma. I mean, I use sigma to get Y1 and Y2. Now, most of the cases where I have solved it, Y1 and Y2, by default, I get them as orthonormal vectors. So suppose in some case, do they always come out like that? Or if they don't come, should I normalize them all again?
They are orthonormal.
They are orthonormal, right? So in some cases, if I don't get them as orthonormal, I have to normalize them, right, sir?
Right.
Yeah, fine, sir. And sir, I mean, in graded assignment, we saw different dimensions of A, the matrix A. So what should we expect in exam? Because the 2 by 2 is easy to solve, but once it goes beyond that, it becomes a little difficult.
Right. So if they're asking you for this SPD form, mostly it will have form like 2 by 2 matrix. Okay. They won't go much further.
Fine, sir. Yeah, thank you.
Okay.
And
So
one small thing, sir. Continue. Like if that matrix is, let's say I saw a graded assignment, I saw a matrix. So for SVD, I saw 3 cross 4. So now in the lecture, professor has found x1 and x2 by using A transpose A. So if I, instead of that, if I find those y using A transpose and use the same process for finding x1, like A into y1 by sigma, can I do that?
Yeah, you can do that. You just have to do the opposite of it.
Opposite, yes, sir. I'm just
from y1 you need to find this x1.
Yeah, from x1 I am finding y1. I'm saying from y1 to x1. That
Yeah,
I can
yeah, you can do that.
Okay, sir. Thank you.
Okay. So we can move on to the week 6. Yes, Vishal.
Yeah. Thank you, Ram. Yeah. Okay. So I'll share the screen. Yeah, so are my screen visible, right?
Yes, sir.
Yeah. So what is that?
Yes, sir, visible.
Yeah, so for quiz 2, we are not providing the mock, first of all. This time, like many of the courses, for the diploma courses, we are not providing, right? So this time we are not providing the mock for the second quiz. So that's why we have not uploaded now. So yeah, so in the 6th week, mostly
Sir, I was wondering that where can we find the solution of the last term quiz paper?
Quiz first, right? So no, many of you have commented like
for term 3, I mean the September term, that was September 2021 term. Where can we find the solution of quiz 2 for that term?
Okay, for that term.
Yes, sir.
I don't know because I was not there that term, so I can't say anything about that. Yeah. So for this term, I can tell you for quiz 1, we have uploaded the solution. But what I'll say, you just focus on the 5 to 8. So from 1st to 4th week, there will be only 1 or 2 questions. So you should more focus on 5 to 8.
That is also small question, right, sir?
Yeah, so that will be like if 1 or 2 questions maximum. That will also consist of some questions that are very much common to 5 and 6 and 1 to 4, like eigenvector, eigenvector sort of things. Those you've already learned from that. So
Okay,
those you can't say perfectly that is from week like 1 to 4. Okay. So in the 6th week, so you don't have any like query regarding the quiz 2, right? So the mock we are not providing, and yeah. So and for the solution quiz first, it's already uploaded. Okay. So now we'll discuss the concept, or we'll just go through the week 6 in brief, and then if you're having any doubt, you can ask. Okay. So in week 6, we are just talking about the positive definiteness. Okay. So that is generally a function that when like it's generally vanishes at 0,0 and is strictly positive at all the other points. Like it's always greater than 0 for all the points. It's not like these are the 4 conditions. Like if you are having this sort of a function, okay, that function can be written in the form of matrix also. Okay. And if you have to convert, like if you have to convert some sort of function into matrices, if you are having the options, you can directly multiply and get the function, right? So you don't have to worry about that. And so these are the 4 conditions, 4 or 5, you can say.
What do you mean by the function vanishes at 0,0? I mean, does it become 0?
The function is vanishes like 0,0. There will be some sort of maximum, minimum sort of things, right?
Okay.
Yeah. So these are the 4 conditions. If you are having the function in the form of this x square plus 2bx y plus cy square, you can write this in the matrix form. And these are the conditions. Like if a is greater than 0, that means the graph you can just imagine in your mind. If a is greater than 0, so it will go upward or downward, right? And if AC is greater than b square, okay, AC is greater than b square, then it's a positive definiteness. Okay, it's, you can consider this as a ball at 0,0 as a minimum. Okay, so in this function, a will be greater than 0. Okay, so sort of things 2x square, some sort of things, and AC will be greater than, AC is greater than b square. Like it's always greater than b square, not equal to, and whenever it will follow equals to. So AC whenever it's equals to b square, that will be a semi-definiteness. Okay, that will, like for example, it's a like it will consist of a one sort of like more number of values where the value like at 0,0 sort of like you can consider one a valley sort of things where a valley 0,0 will consist of more of a points, right? Here only one sort of points will be there that will like represent you the maximum minimum in the positive definiteness. And if you are having a less than, so here one more condition can be can happen whenever you are having the ball in the opposite, like it's like tilted opposite, like where a is less than 0. So at that point it will be a negative definite. Okay. And the third condition is if a is less than 0 and AC is equal to b square, that means it's already from this condition you can consider okay, a is less than 0, that means it's a tilted ball and it will go downward. So at 0, 0 it's a maxima, and for all the other values it's a negative, so it's a negative semi-definite. Okay, so you won't be having any problem in, and if you are having AC
so
less
what
than,
is the meaning of SD? I'm sorry to interrupt.
Which one?
What is the meaning of SD and what is, like, is it PSD?
A P is positive semi-definiteness and negative semi.
Okay, sir.
Yeah.
All right.
And if you are having AC less than b square, so it's a saddle point, or you can say it's an indefinite. You can't say anything about the graph. Like for some values it can go downward, or for some values it can go upward, and you can, like a 0, 0 it generally can be a minima, can be a maximum. We can't say anything about that. So it will come under indefinite, or you can say that there's at 0, 0 there is a saddle point. Okay, so till now you don't have any issue, right? If you're having, you can ask. So till here.
Sir, I find difficulty in converting equation into the matrix.
So what I'll say, if you are having equations and if the given 4 options, you'll be able to convert that in the matrix, right? But if you are like wondering to know how to convert, so there are some articles you can go through that. Okay, it's not the like what I'll say here, if you are having sort of the given equation has been given, so you can just because they can't directly give, they'll be giving you some sort of options, like 4 options will be given to convert this matrix into some sort of functions, right? So you can directly convert that. So you won't face any problem. If you have been, like, for example, I will give you some examples like 2x² plus.
So by a trial and error method, we will have to find.
Yeah, you have to use the hit and trial, then only you'll be able to. Okay.
Okay, sir, okay, sir.
Yeah. So So, and one of the most important thing, you have to consider the matrix should be a symmetric matrix, right? So otherwise it will not work. So the one and most important things that you should keep in the mind, the matrix should be positive. The matrix should be symmetric, right?
Sir,
if the matrix is not symmetric, this things can not work. Okay, may or may not work, but for the symmetric matrix, it will work for sure.
Sir, even if it is 3 × 3 matrix, it will be symmetric.
If the matrix is symmetric, then only you can, with this conditions, you'll be able to tell whether this function is this matrix is a positive definite, or it's a semi-definite, or it's a negative definite sort of things, right? If the matrix is symmetric, then only you'll be able to say anything. Otherwise, you won't be able to. Other condition, if the matrix is not symmetric, so it can be or can't be. Okay.
No, right? Sir, this will be applicable for 3 × 3 matrix also.
Every matrix it will work.
Okay,
if the matrix is symmetric.
Okay, okay, sir. Thank you, sir.
Sir, in some article I found, sir, Sir, this is Mari, sir. In some article, I found that a positive definite matrix is a positive definite function is those function whose value is greater than 0 for other non-zero points and 0 at 0 points.
Yeah, that is what I have said. No? For it vanishes at 0, 0, and it's strictly positive for all the values of all the other values. So that means what? If you are having some sort of ball, so if you are having this function, this is a plane, you can say inside P. So for this point, for 0, 0, it's 0, and for other values, or for all the other vectors, or you can say all the other points, its value is greater than 0, right?
Yes, sir.
So this is what we have said. Positive definite means what? So at 0, 0, there will be some sort of minima. Okay, and for all the other values, it's greater than 0. And if you
in positive semi-definite function, this function can
so this will be sort of a plane, sort of like, see, this will be I'm talking about now a ball for the positive definite. Okay, for positive semi-definite, it will be some sort of valley. Okay, so valley means what? For many of the, like, there will be some sort of planes where all the value for all those values, for all those values on the plane, the value will be 0, right? Are you getting my point? So you can sort of the amount valley you are understanding, right? For the values, there will be sort of a large number of points where the value where x, 0, x, y will be 0. Like there will be some sort of plane, you can say, or line where the values where for all those points the values will be 0. Okay, so you can just understand like this. This is a sort of ball, and this is the value. Okay.
When, sir, the value of function might be 0 at other non-zero point also.
For semi-definite.
Yes, sir. For semi-definite.
Yeah.
That's the thing.
Sir, what if the parabola doesn't come to the 0, 0? It returns back from the 0, 1.
Yeah, so from there will be some values where you will get some sort of, like, whenever you will take the first differentiate, you'll first like what you can say, you'll take the first derivative, right? And yes, the first derivative should be 0. So all the, like, if the function is in the form of xy, so you just have to differentiate for like one time, and you will get the point where the function will vanish. It's not compulsory 0, 0. It will vanish at some sort of point, like the ball is here, and the point is, this point is 1, 1. Okay, and for all the values, other values, it's greater than 0, right? So this is also semi-definite. Yeah, so for if A is less than 0 and AC greater than B squared, so it's a negative definite. Yeah, it's correct.
So the matrix is 3 by 3, and if we want to know if it's a positive definite, then we just need to check if its determinant is greater than 0 only, right? If it's greater,
this is the one test. That is the one test. There are some other tests I'll discuss later.
Like, we don't need to do eigenvalue test, right? Like we can just tell it from the determinant only, right?
So you have to get all the determinant. Like if you are having 3 × 3, so there will be, like, if you are having A1, A2, A3, A4, A5, A6, A7, A8, A9, right?
Yes, sir.
So you can't say directly with the, like the determinant of this matrix is greater than 0. That is fine. That is the one condition. So you have to check whether this pivot is greater than 0 or not. And again, you have to see for all the determinant, like for this determinant. And again, you have to take 2 cross 2 for this determinant if the value is positive, and you have to check for the 3 cross 3. If all the 3 values are positive, then you can say this is a positive. Okay. Or otherwise, you can just calculate the eigenvalue. If all the eigenvalues are positive, you can say. Okay.
Sir, for more than 2 variables, right? Let's say x1, x2, and x3 are there, and the equation is like something like 2x square, 1 square minus 2x1, x2 plus x2
Okay.
square.
Yeah.
So for that, how to write this matrix ABCD?
It's also sort of what you can say.
You can do, in that case, you have to calculate that Hessian matrix. Like the first element is something like dou square up by dou x square or dou x1 square, or like that only. So I had given an example in week 8. Have you seen that? Okay.
In which week?
Yeah.
Which
See,
okay.
Yeah. So Jimmy, you can say regarding.
Yes, sir. You had given an example.
Yeah, to calculate that Hessian matrix. Okay. I think.
Okay. Yeah, this is, I guess this is in the form of this, right? So for 2 matrices, this is simple, like.
Yes.
Yeah. For two like that.
Let's say x, y, z is there, then what to do?
If it is x, y, z, okay. Let me just share the screen.
Okay. So so you can discuss it, like it will be discussed in the when you will take the session, right?
Yeah,
like at 8. Okay. At the end.
No, but here if okay, so that
A
will
3
be
by 3 matrix also, please share.
Yeah, he'll do that. He'll do that for 3 cross 3. How to write this? Like how to change the function into matrix. Okay. So I'll just go through the rest of the. Otherwise, it will take a lot of time. Okay. So you can just remember, Jimmy. He'll discuss. Okay. So now, so for 2 cross 2 matrix, you'll be able to, like, if this is the matrix, you can directly write the Hessian matrix in the form of, right, this xy and yx and fy, right? And then for all those conditions, you can check. So till here, I guess nobody is having any issue. Then if you are having the function, you can calculate the stationary point, right? With, like, you just have to do the differentiate, take the first derivative with respect to all the variable and equate it to 0, and you'll get the points where the stationary point is happening. And to know about the stationary point, whether it's a maximum or minimum, you just to see whether it's a positive definite or not. If it's a
fx is first derivative, right?
Yeah, you have to
xy first partial derivative with respect to x.
Yeah.
Okay.
And with the second is like how many, like whatever the variable, how many the variables you are having, you have to differentiate with each of the variables and then equate it to 0 to get the values of x, y, z, or if you are having the variable, whatever the variable you are having. Okay. So to know about the maximum minima. So if you have to just you can visualize in your mind. If you have to see, you have got the stationary point. Okay. Now you have to see whether it's a positive definite or negative definite. Okay. If it's a positive definite, for sure the stationary point would be minima, right? And for the negative definite, it should be a maxima, right? Because for the positive definite, the function would be like this, right? So this stationary point will be a minima, and for the what you can say, for the negative definiteness, what you can say, yeah, plot, this value would be a maximum, right? So that is what has been written here. So you can, if you're having some sort of a function, so you'll be able to know regarding the maxima and minima. And if you are not able to, like, so if you are not able to know regarding the like the stationary points, like you can't say regarding the maxima and minima points, so that will come under indefinite, or you can say the saddle point there. So these are the conditions. If 0, 0 is stationary, or you can say the whatever the stationary point you are getting, and a is greater than 0. And for all the values, x transpose ax is greater than 0 for all the values. That is simply a condition for the positive definite. So at the 0, 0, 0, at 0, 0, it's the minima, and for the negative definite, it's a maximum. Now we'll move to know regarding the positive definiteness. So one method you can do if you're having the matrices. Okay, A1, A2, A3, A4, A5, A6, A7, A8, and A9. So if you are having this as a matrix, okay. So what you can do, there are 3-4 methods. Like I'll discuss the two important one. One thing is to calculate all the eigenvalues. So and this you can I'm talking about all the symmetric matrix only. So here A2 is equal to A4, A3 is equal to A7, A6 is equal to A8. Okay. So I'm talking about the symmetric matrix only. So don't get confused if the values whatever I have taken is different. So it's a symmetric matrix only. And yeah, so first what you have to do, if you are calculating the eigenvalues, and if all the eigenvalues for all these cases, if lambda 1, lambda 2, and lambda 3, this already we know for the symmetric matrix, all the value lambda will be real. Okay, and all the lambdas are what you can say positive. So this real will always happen because it's a symmetric, and if all the lambdas are greater than 0, so you can say it's a positive definite. Okay, this is the first method, right? And the second method is to know regarding the pivot value. That is similarly, that is like if you have A1 is positive, then check the determinant for the next one, the 2 cross 2 one. If A1 into A5 is greater than A2 into A4, that is positive. Then check the determinant of the whole matrix, like 3 cross 3, and if all the 3 values are positive, then you can say it's a what you can say it's a positive positive rate.
So could you please explain the lambda 1 part again? I mean, what exactly is that?
Okay, so this is not lambda, all the lambdas, lambda I. So what I have told for the symmetric matrix, generally you already know that all the lambdas will be real. Okay, now you have to check whether the lambda, the real lambda, whatever you have got, is positive or not. If it's a positive, then it's a this matrix is positive definite. Okay. Have you got the point?
Yes, sir. And how do we calculate that? It is again like as you said, A1 into A5 is greater than A2 into A4.
Okay, so lambda you can calculate like eigenvalues. Generally, you know how to calculate.
Yes,
A minus lambda equals 0. This is the one method, and this is the sufficient method to say. But if you want to do it quicker, okay, so what you can do, you can just go. You can see, okay, A1 is positive. If A1 is positive, if A1 is negative, then you can directly say it's not a positive definite. Okay, so if A1 is negative, right? Sorry, A1 is positive. You just go through the this 2 cross 2 matrix. Okay, if this 2 cross 2 matrix is having a positive determinant, this 2 cross 2 means A1 into A5 minus A4 into A2, and this is having positive, then go for the determinant of this matrix. If this determinant what 3 cross 3 determinant, if that is also positive, you can directly say it's a what you can say positive definite. Okay.
Sir, does this require A5 and A9 to be positive?
No.
Means only A1 must be positive.
Wait. Yeah. So
because
so the third also, the final determinant should also be greater than 0 for this 3 cross 3.
Yeah. For all the determinant, all the 3 determinants should be greater than 0. So we generally write it as like A1, and then we calculate the determinant upon the A1. Okay, so A1 is greater than 0, then it's a positive. Okay, and the third one is the determinant of the last one, that is all the 3 values upon the it's already positive. So yeah, no, you don't require A5 and A9 to be positive.
Okay, means A1, A5, and A9 should be positive, must be positive.
No. A1 and determinant of this 2 cross 2 matrix.
Okay, and determinant
of this 3 cross 3 matrix.
Okay.
Okay, that should be positive, then you can say.
Okay, sir.
What if A1 is equal to 0?
Hello, sir.
Yeah.
If A5 is
0, I think is considered as positive number.
So can you give an example?
If you're facing any, okay, but the example, okay, I have to check because, okay.
See, can I say?
Yeah.
So what was the question? If A1 can't be 0, if you will you just draw a matrix, and if you put that A1 equals to 0, then it won't be positive definite. You just try out. Okay. So A1 equal to 0, it doesn't satisfy the conditions, because if A1 is 0, just check that it won't satisfy.
First determinant will be negative.
Yeah.
No.
So, but any of the other determinants, if it is 0, also it will not be positive.
If this is 0, then yeah, for sure the first determinant will be 0.
What if A is also 0? Then we get 0.
One?
Then, like A1 and A2 both are 0.
Then calculate the eigenvalues of all the values. And no regarding. Okay. So if so that's the one thing I've told you. And if you are putting all the conditions here, then calculate the eigenvalues. And then if all the eigenvalues are distinct and greater than 0, like greater than 0, then you can say it's a positive. Okay.
Okay, sir.
Yeah. So, but what I told you, it's a simple method to calculate. Okay. So yeah. So it's clear, right? I can move to the next part, huh? Or
yes,
is there any issue regarding that? So
clear, sir.
Yeah. So yeah. And these all are for the symmetric matrix. Like if you have been given a symmetric matrix and then you have been asked, so you should not again tell after the exam why the answer was incorrect, because we are all talking about the symmetric matrices.
This pivot values is just dividing by the determinants. Like A divided by A1, the second determinant, and the third divided by the A2. That's it, right?
Yeah, but that is to check the positive thing. So if you're not dividing also, it's fine. So like, for example, this is the one example, -1, 0. -1, 2, -1, and 0, -1, 2, right? So if you are calculating the eigenvalues, it will take a bit time. So it's better to, this is positive, right? And if you are calculating the determinant for this 2 cross 2, that is what? 4 - 1, right? That is also positive, right?
3 by 2 will be the pivot value. 3 by 2. Yeah. Okay.
Yeah, the 3 by 2 will be the pivot value, but I'm just saying because 2 was already positive, so I'm just saying.
Right. Got it.
And then 3 cross 3 also, if you'll calculate, it will be a positive, right? So 2 into 1.
Right.
Yeah. So the last 3 cross 3 matrix, if you are calculating, because this will be 0, so again it will come as 3, 1, 2. So all the values are positive, so it will be positive definitely. So whoever was asking so many conditions, so are you clear with that, right? Because it was pretty simple. 2 was positive, and then we have calculated 2 cross 2, and it was 0 here. So we have directly say it's a positive definitely. Or otherwise, if you want to calculate the eigenvalues also, you can calculate the eigenvalues also. You'll get the eigenvalues. I don't know what is that, but if you want to calculate, you can calculate. All the 3 values will be positive. Okay, so each of the conditions.
If the matrix, sorry, sir. If the matrix is not symmetric, then we can't do all of these. Is it?
Yeah, then you can't say anything about that.
Okay. Okay.
Yeah. Because for the symmetric only matrix only we are talking everything, right? And for the unsymmetric matrix, again you have to check so many conditions, right? Because here we were having so many other already conditions, like the eigenvalues were positive, like real values and all we were getting. So yeah.
So for an asymmetric matrix, if we get all these conditions true, still we can't say that it is positive definite?
Yeah, we can't say.
We can't say that. Okay.
Can be, yeah, it may be or may not be.
Okay. Okay, sir. Yeah.
So it's done.
So this last one, XTAX, this one. So we will have to carry it for each and every eigenvector. We will have to do this individually.
What? Can you repeat
so
that?
This last third one, no? The last third condition, XTAX.
This one, X transpose
Yes,
AX.
sir. Yes, sir. This is for individual eigenvectors we have to do. For all eigenvectors, you have written for all X. That means individually for eigenvectors or for all eigenvectors, we will have to calculate this.
This is not, see, all of the 3 conditions are necessary and sufficient. Like you don't have to do all the 3 to get the positive definite. Okay, if you are if one condition is satisfied, this is positive definite. So each of the condition is sufficient by itself. Are you getting my point? Like you don't have to check all the conditions. One thing, if you are checking only one conditions and that is coming true, so you can say directly positive definite. Okay, this is the point just I've written. This is like, I guess it's not or not.
This
I don't know.
This X can be any matrix,
values,
right? Any value. Right?
This is simply, sir, this is the equation, right? If this equation is there and it's positive for all the, like this is the equation, okay? And this is a ball. And for all the X values, this is greater than 0. So directly we can write, right? It's a positive definite, right? So that is what I have written. You don't have to check.
Sir, should it be greater than 0 or greater than or equal to 0?
Greater than 0. It's not equal to. If it's equal to 0, then it's a.
Because.
Yeah.
Because at stationary point it will be 0, right?
No, stationary we are not taking. at a stationary point, see, for the graph, this at the x is you can say in the graph, if you are taking x equals to 0, then it will come under, you can say, that example, like valley example. It will not be a ball then.
But for the function to be positive definite,
at a stationary
the
point,
condition is that at stationary point it will be 0, and for all the other points it will be positive.
No.
Right?
So the stationary point is what? If you will take the differentiate, if you will derivate, okay, with respect to all the variable, at that point it should be 0, right? See, have you got the point? Like if you are having some plot, okay, if you are differentiating.
Yes, sir. The idea is that the slope should be 0. Basically, it should be some minimum.
Yeah.
Yes, sir. So, so basically, when we are doing x transpose AX, it's basically, we are simply getting back the equation, right?
Yeah, this is the equation of the plot.
We're simply getting back the equation, right?
Yeah, this is the simple equation. That is this equation.
Yes, sir. So for this equation, if there is no additional constant term, then at some point or points, set of points, the function will take the value of 0.
If that is taking the value for many points, okay, so it will be a semi-definite.
It will be semi-definite. So if it takes for a single point, that will be the stationary point, and that at that point the function will evaluate to 0.
Yeah. And then it's a
that's why I was confused with
then it's a positive
AX to be more than 0 or more than equal to 0.
It's more like greater than 0 only, we write. Okay. So yeah, so we are done with this positive definite now. I'll loop to the PCA part. Okay. So I don't think so. Yeah.
Sir, I asked a question regarding the conversion of equation into the matrix form, and you said that this matrix A will always be symmetric.
This matrix.
Yes.
Yeah, this matrix should be like symmetric. Then only you can apply these all conditions. Yeah. So this should be symmetric.
Suppose only equation is given, nothing given about whether this equation is positive definite or anything. Like in the graded assignment question number, graded assignment 6, question number 5, only equation is given, and they have not given that whether it is a positive definite or anything else. Just we have to convert this equation into the matrix form.
Okay, so that will be taken, like in the end, Jimmy will say how to convert that. Okay,
sir. Thank you, sir.
Yeah. Okay, so now I'll move to the PCA part. Okay, so
one more thing, like you've written like X transpose should be greater than 0. So that means that this 1 by 1 matrix should have all values greater than 0, right?
Which matrix? This matrix?
No, X into A into X.
X into A into X transpose. This is
should be greater than 0. What does it mean?
This is like this is a plot. Okay, one plot is there for all the points for all the X. This plot should be greater than 0. Like for example, this is a ball. For all the values X, whatever we are taking, X the point, all the points we are taking. So this function should be greater than 0. This is what we are talking about. So this is a X transpose AX generally will represent the energy conserved by this plot. That I guess is not taught, but I just wrote here. It's simply the energy conserved by any functions. So the energy conserved by the function is positive, then it's a positive definite function. Okay.
It will be like a 1 by 1 matrix, right?
It's a vector, so it can be like of d-dimensional, right? Like for 3-dimensional, it can take x1, x2, x3, right?
And those values x1, x2, x3 are greater than 0. Then.
So those x1, x2, x3 should not be greater than 0. It can take any values. Okay, when we are putting in the equation, the values on the end should be greater than 0 for the positive definite. Okay.
Yes, sir.
Yeah. So don't get confused with that. Should all the conditions should be there in the mind. If you are not able to convert this, you'll be able, like with the in the end, Jimmy will discuss that. But I'll say if you are not able, if for 2 cross 2, you should not face any problem. Like you can directly write the fx and fxy, and then like see, this is the condition fxx, fxy, fyx. This is same, and fyy. This is what you are just differentiating. After differentiating, what you will get? You will get 2a, right? So all this condition, whatever I have written, will satisfy for this also. So fxy will what? B will be 2b, right? And here also you'll get 2b. And here also you'll get what? 2c, right? So the same condition, like whatever I've written, so you can directly write for the wherever I've written a, you can directly write this fxx, and for all the conditions, like it will satisfy all the condition wherever I have written fx, you can just replace with a and fxy with what you can say b and fy as c, and then you'll check all the condition, you'll get to know regarding the PD or PSD or NSD. Okay. So don't bother about, like, don't think much. So you just have to, if you are having the function, if you are given the function, just check the values of A, B, C. Okay. And if you have been given matrices, so if you have been given in the form of matrices, that is also pretty simple. Okay. To do that, you can, I've told you two tests. You can calculate the eigenvalues or you can check the pivot values and we'll be able to, right? So I'll move to the next part now. So I don't think so now you're having any issue in this. So the PCA, yeah. So the PCA, in generally why we are using the PCA to simply for the visualization. If you are having the very large dimension of the equation, like very large dimension in the data set, so we just have to reduce the dimension so that we can train the model also and we can visualize the things also in a better way. Okay, so now we will go through the geometric interpretation. Okay. Okay, I'll go through that. If you face any problem, okay, you may let me know. Okay, so I'll explain the whole thing about the PCA, the basic concepts, and if you're facing any problem, whoever has asked the question, you can ask me. So the geometric intuition of the PCA is what? So I'll just I'll talk about the what you can say, the 2-dimensional, and that I have to convert in 1-dimensional. How I'll do that? So if I'm having 2D of the data set, and the data set in the one data set, one feature is that. So if I'm having data set which consists of F1 and F2 only. So I'm having 2 features only, the data set I'm having, and having 2 features only, F1 and F2. So the one feature is first the blackness of the hair. Okay, the one feature is the blackness of the hairs, and everybody agree with me. Okay, so if this data set is regarding the India, okay, so mostly the blackness of the hair will vary from what, gray to black. Okay, so there is not much of the spreadness in the data. Okay, if we'll just convert this blackness into some, normalize those values and we'll convert this from 0 to 1. So you'll get to know all those values, like whatever the normalized value we are getting for the blackness of hair, will lie from some sort of, like, we can say, if I'm taking black as totally 1, so gray will lie from what, 0.9 to 0.1, like 0.9 to 1. So all those values, whatever I'm having, all the data set, the values of the blackness of the hair will lie from what, 0.9 to 1. So the spread is very less in this case, right? So you can see the spread is very less for the blackness of the hair. And what is that? The second feature is the height of the person. So we are just having 2 set of features, the blackness of the hair of the person and the height of the person. So whenever the height, so we can see the spread of the blackness of the hair values and the spread of the height. So if I've been told, if I'll ask you to remove the one features, okay, so we can just tell you, okay, the spread is very less in this blackness of the hair, because every time the blackness of the hair of all the person is almost same, right, from 0.9 to 1. So we can remove the one value, right? So the spread of the blackness of the hair can be removed, right? So if you have to convert this 2D into 1D, so we can directly remove the F1 and we can directly say, okay, we are having just the height for all this data set, right? So what we have seen here, wherever the spread is very large, so we have to consider, we have to keep those values, and wherever the spread is very less, that means what? If I have the data, and for all this data, the height of the person is generally 6 feet. It's like from 5.10 to 6 feet. So we can just tell, okay, the height is almost same for every person. We can remove that features, right? So we can just remove that feature and we can convert this 2D into 1D, right? Now to just visualize it in a better way, right? Like if I'm having a D dimension, D is very large, and if I in that D features, there are many features which are very much similar, or we can say the spread is very less, so we can directly remove that. That is the one thing about the PCA, right? So if I have to convert this 2D into 1D, we can directly remove those features which are having the very less spread, right? So till now you don't have any issue, right? Are you able to hear me or not?
Yes, sir. Yes, sir.
Yeah. So yeah. So the basic concept behind this, we have to just reduce the dimension. Like here, what I did, I've just what I did. Oh, okay. So yeah. So what I did is, I've just reduced the dimension from 2D to 1D. Okay. So what we have did, I skipped the F1. Okay. Now we are having the F2 only. So by reducing F1, we are losing very less information, right? Because the spread is very less, so we are losing very less information here. So what is the basic fundamentals? So we have to lose the information, like we have to lose a very less amount of information while doing this PCA. Okay. Right, and we have to preserve the direction with the maximum spread. So what we have to do, the three basic things what we are doing, we are just keeping the spread, keeping the dimension, or you can say keeping the features wherever we are having the maximum spread. We are removing those features wherever the spread is very less. Okay, and we have to just get the direction in which the spread is very large. That is what we have to do till now. Yeah. So now, for example, again, I've taken one example with F1 and F2 as the features, and here the data set are like this. So here the data set is not that simple as like this, because here the data set was pretty simple. We can directly remove this one, and we can get the height as only one features, and this would be the, what you can say, the direction where the variance is maximum, right? Or you can say the spread is maximum. So I'm just interchangeably speaking the spread and variance. Okay. So whenever I'm saying the spread, you can consider this as variance also, and wherever I'm saying variance, that is spread. So here I'm having F1 and F2 as two features, right? So F1 is one features for the data set I'm having, F2 is the other features, and these are the data points I'm having. So these data points, you can see, you can say whatever the concept I have used in the first one, you can't say anything regarding, you can't use that concept in here. So, but here what you can see is, you can get a direction like F1 dash and F2 dash, you can plot, and you can see that in the F1 direction, when you have projected all those data set in the F1 dash you can consider as one direction, just a one vector or a direction. Okay. So if you will project all those data set in F1 dash, right? If you are after projecting those data set, you will see that in the F1 dash, like if you will project all those data set, you'll see that the spreadness of this point, all those points, is this much, right? And the spreadness in this direction is this much, right? So what you can do here, you can just rotate this. What you can say, this you are having two direction now. You can just rotate this direction, there won't be any issue. And after rotating that, you saw that in this direction there is a very less spreadness, and in this direction there is a very large spreadness. So you can just remove the F2 dash, and if you can just keep the F1 dash, or you can just know regarding the direction of the F1 dash. So you are very much you are very much able to convert this 2D into 1D. That is what generally we do for the larger dimensions also. So here I'm having 2 dimensions. I've just converted into 1 dimension. What I have did, I've just taken all the projection of all the point on the unit vector, all the projection of the points on a direction where the variance is maximum, and we remove the other direction where the spread is very minimum, or you can say the variance is very minimum. And we have just dropped out the F2 dash, we have kept the F1 dash, and that is what you have to know regarding the direction of the F1 dash. Okay, so we have to just know the direction of one dimension. You have to just know the direction where the variance is maximum. Okay, and that is how we are converting that 2D into 1D, right? So till now you don't have any issue, right? So you are getting the point regarding the PCA.
Yes, sir. Clear.
Yes.
Very well explained, sir. Thank you.
Yeah. So right. So now what we are doing. So now what we want is, we have to find the direction of the F1 dash such that the variance of the xi projected on the xfi is maximum, right? So we just have to get the direction of this x1 dash, F1 dash. In the lectures has been talked about u1. So don't worry about the whatever the point, like what you can say, the figure or whatever the values I'm taking. So here in the lectures, every time sir has taken like U1 or U2 sort of things, I've taken F1 as a, so that F1 generally will represent the features of all the features. So F1 dash, you have to just find the features, or you have to just know about the, okay. So you just have to know regarding the direction of this, what you can say, direction of the vector, wherever the variance is maximum. So this is what we have to do to find the direction F1 dash, so that the variance of the xi projected on F1 is maximum. Okay.
So this, can you just go on top? The
Okay.
Yeah. Actually, this figure actually makes it very, very clear, because if we project these points on F1 and visually, we can see that the reconstruction error will also be minimized on F1, then on F2. F2 will be more.
Yeah, correct. You are very much correct.
Thank you, sir.
Either you are talking about the variance or the reconstruction error, both are almost same. Okay. So if you're talking about the variance also, that is same. If you just go and do some sort of mathematical things, you'll get to know whatever the reconstruction error, whatever the values in the end you were getting with the help of Lagrange multiplier and all, in the end, after solving that, you'll get the same direction.
Right.
That is the maximum, that is the eigenvector corresponding to the maximum eigenvalues. Okay.
Right.
So both are same. So you don't have to worry about the reconstruction. Those, I can say, the both are the two way to go in the end, like whatever you can say, like two way to conclude one thing. One is the reconstruction error, minimize the reconstruction error, or to maximize the variance. Both are same. Okay.
Right. So now visually it's also clear with this diagram. So that's why thank you. Thank you for sharing.
Yeah.
And so the maximization of the variance is so that we can enclose more number of points, right?
Not enclose more number of points. Oh, can you elaborate that? Like.
So if the variance is more, which means that you are including more number of points, so you have a bigger data set. Is that the reason? Why do we think of more variance?
No. Variance is just so that, see, variance is variance is what? The spreadness of the data, right? Are you getting me? The spreadness of the data in some particular vector or some particular direction. Yeah. So I'm just taking this direction so that I can see the variance is maximum in this direction. So I'm not talking about the points. Okay. So in this direction, all the points, whatever the points I'm having. So you can say the most of the points, not all the points, because all the data set generally it's not very much fine. So you can conclude the most of the data set. But if you are projecting on some direction, you are getting the variance as maxima. You have to just know regarding that vector where the variance is maximum. You'll get some sort of other vector, other plot also, other, what you can say, vectors also corresponding, because if you're having a D cross D matrices, so you'll have D eigenvector, right? You'll get D eigenvector. So you have to check whether which of the eigenvectors I'll get after solving this optimization problem, so that I'll be having the maximum variance. I'll not lose the information. Like, for example, I'm having two lambda as lambda 1 equals to 5 and lambda 2 is equal to 10, right? So I'll just, for example, I'll tell you. So I'm having two D cross D here is 2. So I'm having 2 cross 2 matrices, and I've got lambda 1 is equal to 5 and lambda 2 is equal to 10. So I'll take this variance. I'll take this eigenvalues, right? I'll take the direction of this, what you can say, the direction of the eigenvector corresponding to this eigenvalues, right? Yes, sir. So how much information we are preserving? We are preserving 10 upon 15. So that means what? 3 upon 2 upon 5, 2 upon 3. So we are preserving almost 66% of the information, right? Okay. So we are losing the 33% of the information. So if I'm taking this eigenvalue, eigenvector corresponding to this eigenvalue, so I'm preserving only 33% of the information. So that is not the correct direction, right? Okay. Yeah, got it, sir. Yeah. So yeah. So this much is clear. So PCA this is what generally you have to visualize. You just have to two things is that. So you can now all things are just, you can go through like the, what you can say, the lectures also, how to like use many of the concept to just conclude one information. This is what you should be having there in the mind, why we are doing the PCA. This was the most important reason why we are doing the PCA. And how we are doing the PCA, and after that you just have to see the two method can be there. One method is just to get the projection of all the points here, and after getting the projection, this is the optimization problem. This is optimization problem. That optimization problem can be solved with the help of gradient descent and all. There are many methods like Lagrange multiplier. So many methods are there to calculate the eigenvectors or the direction where the variance is maximum. So this is the what you can say that this was the issue that you have to solve.
I have one doubt here. So this the algo, when you work in certain problems, when we calculate the covariance matrix,
yeah,
and we want to find the eigenvalues from that.
Yeah.
And in some problems, what we've done is we've taken a scalar out of the matrix and
Okay.
taken out the, because it makes it simpler to calculate the eigenvalues. So we calculate the eigenvalues.
See,
Now in some problems, when we take out the eigenvalues, the scalar is multiplied by that value, lambda value, what we get.
Okay.
But in some problems, it is not multiplied. So what is the correct procedure?
Yeah. See, one thing, many of the books will say you just have to calculate the eigenvalue of this one, right? If you go through many of the books, that will say, okay, get the x transpose x and calculate the eigenvalues, and you'll get. But many of the books will say to calculate the eigenvalues of the covariance matrix. That means 1 upon n you should consider. Okay. See, one thing is you'll get the direction same every time. You'll not. So eigenvalues can be different if you are taking. See, if you are taking what you can say, if you are taking one matrix as x transpose x, this is what this is, right?
Yes, yes.
X transpose x, if you are taking, so you'll get eigenvalues sort of lambda 1, lambda 2, lambda 3, and whatever the corresponding eigenvalues, eigenvector you'll get corresponding to lambda 1. Okay, that you have to consider direction only. You have to take the direction only. You don't have to bother about anything, the eigenvalues and all. But if you'll consider 1 upon x, x transpose x, so you'll get the different eigenvalues.
Right, sir.
So if in the calculation part, if you have been asked to calculate the eigenvalues of this, you should consider 1 minus 1 upon n. Okay, you should not remove this, because you can't remove this. Okay, I just have to do 1 upon n is in the here, so we can just remove. So you'll get the different eigenvalues for sure, and you'll do it a blunder there. Okay.
Right.
Yeah. So many of the places there are mistakes that have to correct. So in the 6th week, there are the solutions where I can see like whoever has solved that has taken 1 upon, he has just removed 1 upon n. So you don't have to remove 1 upon m. If you are getting the values like 1, 2, 3, 4, and 1 upon 3 is here, so you just go through. So you have to do like this: 1 upon 3 minus lambda, 2, 3, 4 upon 3 minus lambda. Okay, then you have to calculate the lambda. But the final thing, the final vector, you'll get the same. The direction you'll get the same. Okay, there won't be any problem in the direction, but the eigenvalues you'll get the different. Okay,
Right.
got the point, right?
Right. Thank you, sir. Thank you.
Yeah. So I guess this was the issue many of the people were asking on the discourse also. So now I guess it's clear. Yeah. So if you're having 1 upon n, so in the question also, if you have been asked to calculate the eigenvalues of the covariance matrix, if they have been given 1 upon n, then consider 1 upon m. Okay, every time. Otherwise, you'll get the different eigenvalues. So yeah. So this is what has been discussed. Yeah. So now we'll move to the next part, and this is what this was the one method to calculate with the help of variance. You have to maximize the variance and get to know in the. So using the Lagrange multiplier and all, you'll get to know U1 will denote the first factor. If you have to convert that into 2-dimensional, you have to consider only the most valued eigenvalues, and corresponding to that eigenvalues, you have to consider those eigenvalues, eigenvector ones. Okay. And if you have to convert that into 1D only, so you can just take the only one eigenvalue, and then corresponding to that eigenvalue, you have to calculate the eigenvector, and with that you are ready to go. The second thing is the minimize the reconstruction error. That is what he has should. So what is that reconstruction error? One thing is the see, if I'm just dropping this x, this is the x, all the one thing has been clear, right? The variance, how you have to maximize the variance, and you get to know regarding the direction in which the variance is maxima. The second thing is to minimize the reconstruction error, and to minimize the reconstruction error, all these are the all points, and all these points, what you have did, you have just taken the projection of all those points here. So you are having this value, you are having this value, and now you can calculate this reconstruction error. So reconstruction error is this, and for all those points, the reaction, what you have to do, if you have to get this direction. Okay, what you have to do, you have to minimize D, right? So all the D, after doing the summation, you have to just minimize that. right? So what you have did, so you have to just minimize the reconstruction error, the error whatever you are getting. Okay, so this is the problem. You have to minimize this distance, and you have to minimize this what you can say, this distance here. So this is the reconstruction error you have to minimize with the constant u transpose u is 1. That is like we have just considered that the vector we have to consider. We are not bothering about the magnitude, so that's why we have just taken the unit vector. Okay, and after solving this, we'll get to know. So from both the point, if you'll solve, you'll get to know about the same eigenvector that is corresponding to the lambda 1. That is the maximum value of the eigenvalues. That is the maxima. That is the vector corresponding to the maxima of the eigenvalues. Okay. If you have to consider, if you have to convert that into one dimensional, if you have to convert that into two dimensional, you can consider the two most important or the two most valued eigenvalues, and corresponding to that two eigenvalues, we'll consider the two eigenvectors. Okay. So these are the things which are important to remember. The covariance matrix you already know, 1 upon C, 1 upon n x transpose x, right? And the u1, u2, u3 will correspond to the lambda 1, lambda 2, lambda 3, lambda 1. If you have to convert that into 3-dimensional, that is the if you are having if you have to convert that 3D into 1D, so you'll consider only lambda 1. Okay, and the projected data will be xi will be this one, summation of xi transpose ui into ui. Okay, and the reconstruction error is this one. So this is what you have to just remember. You can just solve some of the questions. You can just go through the most important thing. You just go through the solve with the instructor. There are some problems, I know. There are some, I'll just go through that also. There are some issues in the solution wherever the C has been taken, N has been removed. So you just have to see there the eigenvalues will be different, but you will get the same eigenvectors. Okay. Yeah.
Sir, here ui is eigenvector corresponding to the maximum eigenvalue, right?
Yeah. So I guess.
So for 3, do we need summation for each xi? It is.
Yeah. If you are having the vector like x1, x2, x3, like if you are having this eigenvector as like this, x1, x2, x3, then you have to do the summation for all these parts, and you'll get the projected data. So I'll go through the one example, and that will make you clear. Okay. So that was it from the 6th week. I'll share this document. Maybe I'll go through that. It will make you clear. And yeah, I'll go through the. Okay. So in the supplementary thing, I'll upload. I'll tell the team to upload all these things. Okay. And yeah. Okay. So yeah, so this was the question. You're having the data set has been given, right? Data point has been given. So what you have to do, you have to first calculate the mean vector. Okay, so symmetric matrix will be C is equal to 1 upon n x transpose xi. So the characteristic equation, whatever you are, will there be any more revision session? No, there won't be any revision session. So it will go like, I guess 2 hours already there. So it will go beyond, I guess 3 hours. So there won't be any revision session. So yeah. And then what you have to do, so you have calculated the characteristic equation from there. So you don't have to remove that 1 upon n each time. So here it's a mistake. So 2 upon 3 minus lambda 1 upon 3. So every time you have to consider that n, right? And then you have to calculate the lambda. And then from that lambda, because the lambda, the eigenvector will not be different, but the eigenvalues, if you have been asked to calculate the eigenvalues, so you should consider this in mind, 1 upon n should not be ignored. Okay, otherwise you'll get the different eigenvalue, right? And you can calculate the transform data set. Okay, x1 tilde, x2 tilde with the help of this formula, simple formula. What was that? So this was like simple. What was that? Yeah. So that I've written, right? Somewhere I wrote.
Sir, once, sir, please for once explain the step 6.
Okay. So if I have been given the data points, right? So what you'll do first, you'll calculate the mean vector, then covariance.
That I understood, sir. Only the projection and finding the projected value. This part.
Yeah.
This part.
The projected projection on U1 is what? You can do the X. So whatever the data set you are having, you'll just multiply with the how generally you calculate the projection. If you have to calculate some projection on some different vector, generally you take the transpose of one thing and you multiply with that, right? X transpose X, yes. Right? So you get the projection and you just have to multiply with that in the end. You get the projected data point. What?
Multiply that with the given data.
Vector, right? you already have multiplied the you have already taken the vector data point, right, 1 times. So generally the formula is what? Where is that? Yeah. So I wrote it here, right? So this is the simple formula: X transpose UI into UI. So this is the vector.
Yes.
Eigenvector you got. So you just have to for the data point, you have to get the projection first. You got the projection here and then multiply with the vector, right?
Yes,
How generally you get the projection? X transpose into UI. So you got the projection and then you multiply with the eigenvalues, eigenvector, and then you'll get the projected data, right?
This is much simpler.
Yeah. So I guess this for the 6th week it's done. Yeah.
So just one question. So in the explanation and the proof and all that, there were 2 parts, right, of the projected data. There was one where up to m vectors we were multiplying. With,
that was see, if you are having d cross d is the dimension, and okay, so if you are reducing to the m dimension, right? So m was lesser than d, right? So when you have to calculate the reconstruction error, what he has done, the professor has done, he has just the base, he has increased the base, okay, from m to d, so that it will be simpler to project all those d point on the vector, because I have taken the bases which are having only m point, right?
Right.
So now what I have enlarged those things from m to d, so that it will be simpler to project all those data set on the data on the vector, wherever we are maximizing, or what we can say, the minimizing the reconstruction error. Okay, and then he has done. So I guess you don't have to go through the proof now. But
no, so when in case of the problems that we get, if we are asked to reduce the dimension from d to m, then from m+1 to d, we will have to project the mean vector onto.
Yeah. There you have to do, but I don't think so that anybody will ask you to calculate manually, because you can manually will take again half an hour to do that if you have been given 5 to convert that 4, right? So manually, everybody knows with the help of basic Python code, you'll be able to convert. Otherwise, anybody will ask you. If they're asking, you'll just ask to convert the 2D into 1D, right?
Okay.
Yeah.
Because in the examples that we have seen so far, at least in the graded assignments and all that, there was no.
Nobody will ask you to convert manually, right?
Okay.
Yeah. So I guess done from the week 6. So we'll move to the next week, right? So yeah. Ram, are you there?
Yes. Yeah. So we continue with week 7.
Yeah. So week 7. Yeah.
Yeah. Something comment?
No, I'm not asking. Like, you can start the week 7. I guess 6. Yeah. Thank you.
Just give me a second. I'll just.
Oh, okay.
Okay. So. One second. Okay, so what we'll do is I'll go over the slides so that we look at the entire content of week 7. Week 7 is primarily easy, I suppose, but if you still have some questions, you can ask. Okay. So when we look at optimization, right? So we primarily have some function or something which we need to optimize, like either like maximize or minimize. It depends. Okay. So in this particular scenario, this was a co example where the cow needs to go to as close to the grass as possible. Okay. So that's one, and we will not talk in detail about this. Okay, but we will talk about this one, the general form where whichever one we need to go optimizing, right? So that is whether it's like minimization or maximization. So that is called as our objective. Okay, it's called objective function because that's the thing which like that's like our main target, you could say. And to achieve that, there could be some constraints, like this particular scenario, gi of x less than or equal to 0. Here we could have some here we could have k number of equations like this, okay, and similarly we could have hj of x equals 0. This could also be some of the conditions, okay. Here also we could have some let's say like some j equals to 1 to L condition, okay. So these are all the constraints we have to achieve this objective, to minimize this particular parameter, okay. And if you look at the unconstrained one, those are the problems where you won't have any of these constraints, like less than or equal to 0 case, or greater than equal to 0 or equal to 0. Any of those conditions you won't be having, okay. So there you just have this objective function, and then you just need to minimize or maximize it, okay. So so how do you do it? How do you exactly solve for this minimization or maximization problems? We just look at it now, okay. So if you look at the problem here, we have this minimization of x minus 5 whole square, right? So if we plot for that x minus 5 whole square, we are like pretty much aware of it. We have this quadratic equation which is like centered around this x equals to 5. So for us to minimize it, obviously we know that at x equals to 5 only we'll be getting that we'll be getting the minimized value, right? So how do you do it? One obvious way is to do this. We find this f dash of x, and then like we equate it to 0, right? And then we directly get it, okay? And then we'll directly get like okay, at that particular point we'll get the we'll get this f of x as minimum, okay? Overall global minimum. Okay? We'll talk about this global and local minimum also in a minute, okay? But then let's say like you are like doing it in an iterative process, okay? You're not directly solving it, okay? You're doing it in iterative process. So in the iterative process, what you assume a point, like you start with some value of x, and then you move either to the right or left, okay? Like let's say in this particular example, we have started at x not equals to 8. From this particular x not equals to 8, we should move either to the left or right, okay? So such that the next point where we check for this minimum condition is this xt plus 1 equals to xt plus t, okay? So this d value, this d could be either it could be to the right or to the left, right? So we should know which direction to move. So specifically which what would be the good direction to move, okay? So the good direction to move for this particular problem, for this particular minimization problem is minus f dash of x. Okay, minus f dash of x. So we look at it by we look for the scenario of x not equal to 8, and then we look for some other scenario also, and then we will like through the graph we will find out why this by d equals to minus f dash of x is a good direction to move, okay? So at this particular x not equals to 8, if you look at it, the value for the f of x is somewhere around here, right? So the slope of it, that is f dash of x of it at x not equals to 8 is positive, right? Because if you draw a line there, so that would be positive, right? So the slope at x not equals to 8 is positive. But you know that you should be moving it in the opposite direction, right? You should be moving since the optimized value that is the x at which the optimal value occurs is equals to 5 is to the left. So we should be moving to the left, right? So basically, in this particular scenario, we should reduce the xt value, right? So this d should be negative. Since f dash of x is positive, minus f dash of x will be negative, so that we are moving in the right direction, okay? So at x not equals to 8, if we take the d value as minus f dash of x, we'll move in the right direction. Until now, is it clear? Is it clear? Am I moving too fast or too slow? Hello.
Yes, sir.
Okay, yeah. So let's say like okay, we'll take some other scenario. We'll take x equals to 2. Okay, we'll take x not equals to 2. That is a starting point. Okay, at x not equals to 2, if you look at the f dash of x value, that is negative. Okay, that is negative because the slope at this particular the slope of the graph at this particular x equals to 2 is negative. Okay, so in this particular scenario, we know that our optimal value occurs at 5, right? So we need to move to the right. Okay, so basically our d should be positive. We know that f dash of x is negative, So minus f dash of x is positive, so we'll still be moving in the right direction. So we will still be moving to the optimal value direction. Okay. So irrespective of what the value of x is, by moving in the direction of like d equals to minus f dash of x, we are moving in the right direction. Okay. So that's one important inference. Okay. Clear? The derivation part of it, like why exactly minus f dash of x, why not something else? Look at it later. So the others mutual. Okay. The other important aspect is, okay, we are moving in the direction of like minus f dash of x, but then if you take this example of like x minus 5 whole square, and then you are at x equals to 10, right? You'll move to x equals 0 by using this xt plus 1 equals to xt plus d formula. Okay, and from x equals 0 by using the same formula, you will again move to 10, right? And then it will come to 0, it will move to 10, come to 0, and so on. Even though we are moving in the right direction, we are still not able to reach this optimal solution. Okay, it doesn't matter how many iterations you do, we'll still be like oscillating in between, that is like moving in between 0 and 10. Okay, from 0 you move in the right direction, but you reach 10, you cross this 5 value. Okay, from 10 you move in the right direction, but you move directly to 0. Okay, so it's not just the problem of moving in the right direction now. Okay, how much amount we should move, that also matters. Okay, so that's one important takeaway from this particular example. Okay, so after that, so let's say like we know that xt plus 1 equals to xt minus eta t into f dash of x. So sorry, forget about eta t now. Xt minus f dash of x, right? F dash of xt. Okay, so we know that minus f dash of xt, that is the right direction. Okay, but how much to move, that will be given by this eta t. Okay, eta t. So that is a scalar quantity. It should be positive, because if you change the direction, if you take this eta t as negative, right, that means that you will not move in the right direction itself. Right, you will move in the wrong direction. Take eta t as negative. So that's why eta t should always be positive. Okay, and also it cannot be constant. Like it cannot always be constant. Like we took for eta t as 1 in the previous cases when we assumed xt plus 1 equals to xt minus f dash of xt. Okay, it should be it should be like it should depend upon the number of iteration, also the iteration where we are at. Okay? So it should be a function of t. So the way in which you could do is like you can assume this eta t as like 1 by 2 power t. That is one initial assumption Sorry taken. But the problem with that is the steps which you are moving, the sum of all those steps, if you take it eta naught, eta 1, and so on, that won't be the maximum sum of it. That's going to be equals to if you take it, that's going to be equal to the sum of all will be equal to you can't like move on like too much. Okay, you can't move what could happen is you might even stop before you like reaching to the optimal solution. Okay, so this particular scenario, that is this one. Okay, let's say like we are here, this is the optimal solution, and then like we are here at x0. Okay, but we might not even like reach that optimal solution. Okay, in this particular scenario we are reached, but we could be at a we just draw this and explain this. So what we have is this is a quadratic equation. Okay, this is optimal value, minimum value, and then like let's say this is the point where we are at. This is x0. Okay, and then okay, we are moving the right direction by using eta t equals 1 by 2 power t. Okay, we might be at this position. Okay, we might come here. This is x1. Okay, from here to here we come. This is x1, and then from here next eta t is equals to initially t equals to 1, right? So that is half. After that, we might be at 1 by 4. So we might move slightly closer to it. We might come here. After that, we might come here. Okay. Okay, and then and so on, we might not even reach it. Okay, after even, let's say, like you are at infinite number of iterations, you might still end up here. Okay, you might still end up here. Okay, the best possible scenario, even after infinite iterations, you might end up here. You might not even like reach this optimal value because your step size is too small, 1 by 240. Eta t equals 1 by 240. So step size is too small. Okay, the sum of these step sizes will be converging to a particular value. Okay, so that is why 1 by 240, that's not a, what is it, the correct step size for this particular problem to achieve this optimal value. Okay, so to avoid this problem, initially our step size is too small. Sorry, initially our step size is too big, where we took eta t as like 1 itself, and then in the other scenario our step size is too small. Then what would be the ideal step size? So the ideal step size is eta t is 1 by t plus 1. Okay, we are reducing our step size after each iteration, and overall, but the sum of all the step sizes, it will still be equals to infinite. Okay, so that is why eta t equals 1 by t plus 1. That is a good step size.
So one
And
question.
yeah,
The sequence be divergent, like to be a good step size.
what can you repeat?
Should the sequence be divergent for it to be a good step size? Does it need to be divergent instead of convergent? It should not converge to any number. It should be divergent, right?
Yeah.
So, but what about if we get 1 minus 1, 1 minus 1? That is not a good divergent algorithm. So, out of divergent algorithms, you have to pick the best one, right?
You're talking about 1 minus 1, eta t value is 1 minus 1 and all.
Yeah, like sometimes a sequence just gives 1 or minus 1. For example, minus 1.
One of the important thing is eta t cannot be negative, right?
Okay, right.
See, I was talking about this now. Xt equals to xt minus eta t into f dash of xt minus f dash of xt. That is the correct direction to move, right? So you should move in the correct direction, but the thing is, you should scale it. That's it. You cannot entirely move in the opposite direction, right? If you take eta t as negative, you move in the opposite direction, right?
Yes.
So eta t cannot be negative. Okay.
Yes, sir.
Yeah. Okay. So this is the algorithm for this gradient descent. Okay. In the gradient descent algorithm, we use this eta t as 1 by t plus 1. Okay. So after each iteration, the eta will be right. The eta t will be reducing, but we will still be able to reach the optimal solution. Okay. And we won't be oscillating like we did in the previous example. Okay. So after this, look at the next lectures. So the next important part is we have this gradient descent algorithm. The gradient descent algorithm, what it does is we are basically checking for this xt. Okay, where is it? Okay, let's just what we are doing is for each time we are calculating the next value of x based on f dash of x, right? Based on f dash of x. What if this f dash of x equals 0? What if we come to the point where f dash of x equals 0? We won't be able to move further, right? So that will be our optimal solution. Okay, at least that's what the algorithm gives. Okay, that's what the algorithm gives. And the problem is that f dash of x equals 0. That means that it is a local minima, right? It is a local minima. That need not be the global minima. The difference between local minima and the global minima is, for the local minima within a small range, that will be the smallest possible value. Okay. So if we take for the example of this one, right? This one here. So that is a local minima, right? That is a local minima. But the thing is that is in the global minima. If you look at the entire graph of f of x, so at this particular point of x star only, you'll be getting the global minima. Okay, so global minimum. And the problem with gradient descent is if we assume x0 to be here, x0 to be here, then you'll come up like the optimal value or the optimal x value which the gradient descent gives is this particular value. Okay, x hat. Okay, or let's say like you took this value, then the optimal value which the gradient descent gives is this one. But that's not the actual optimal value. The actual optimal value is this extra. So that is the limitation of this gradient descent. So that is why what they say is so gradient descent will be the optimal solution if that function is a convex function. Okay, the definition for this convex function is all the local minima is the global minima. Okay, all the local minima should be this global minima. Okay, then this then that particular function is called a convex function. Okay, so when so since we know that by the gradient descent we will go to this local minimum value. So and since that local minimum is global minimum, we need not worry about we need not worry about whether whatever optimal value we got is like actual optimal value or not. Okay, since it is a convex function, whatever value, like whatever optimal value we get through this gradient descent, that will be the optimal value itself. That will be a global minimum itself. Okay, clear until now? Local minimum, global minimum. Clear? Okay, we'll go ahead.
Can you please repeat the convex function once?
Yeah, so the convex function, the functions where we have this local minima is a global minima, right? Where all the local minima are the global minima, then that particular function is called this convex function. Okay.
Okay, yeah, thanks. But what will be for the maximum, global maximum or local maximum?
We do not care about that. Okay.
Okay, we will deal with only the minimum.
Yeah.
Okay.
The exact definitions or the more elaborate definitions that came up in the weekend and even in weekend also the process for the convex function. Okay. Moving ahead, so we talked about this xt plus 1 equals to xt plus eta d2 minus f by x, which is gradient descent algorithm. Okay, and the Taylor series is the expansion for Taylor series is one where f of x plus eta d equals to f of x plus eta d into f dash of x plus eta square d square by 2 to f double dash of x plus eta square dp by 3 and so on and so on. Okay, the great important takeaway is that so it doesn't matter what value of what value you want to know. Let's say like you know all the information at a particular point, like x equals 0. At x equals 0, you know all the information, like you know f of x value, you know f of 0, f dash of 0, f double dash of 0, f triple dash of 0, and so on, right? So if you know all the information at a particular point, then you could know then you could actually find out the f of x value at any point. Okay, then you could find the function value at any point. Like let's say like you want to find the f of 10, f of 20, f of 100, f of 1000, f of minus 1000 anytime, right? In any value you could find out using this. You could find out using this Taylor series. Okay, that's the beauty of this Taylor series. Okay, where one local information gives the entire global information. It gives the information about the entire function of x itself. Okay, and we talked about the d value as like minus f dash of x, right? Why that minus f dash of x? We talked about it now using this Taylor series. Okay. For us, if we know that we need to find this minimum value, right? Okay, so whatever we have this f of x plus eta d equals to f of x plus eta d into f dash of x and so on. We'll ignore the higher terms because whatever eta d which we choose, that will be like minimum itself. This eta d entire value is minimum. So eta square d square by 2, it will be even smaller such that we can ignore itself. Okay. So when we have this f of x plus eta d equals f of x plus eta d into f dash of x, our condition is that f of x plus eta d, we are moving the x plus eta d is the right direction. So which basically means that f of x plus eta d should be lesser than f of x, right? Since we are opting for this minimum value, f of x plus eta d should be less than f of x. So basically f of x plus eta d minus f dash of x, it should be less than 0. Well, okay, it should be less than 0. Then only we can say that we are moving the right direction. Like we're talking about this particular example, right? Let's say like this is here we have some f of x value, okay, and then this is x plus eta d, this is x plus eta d, and on this particular value is f of x plus eta d. Okay, when we are moving only in this direction, we can say that when f of x plus eta d minus f of x, if it is less than 0, then only we can say that we are moving the optimal direction. So the correct direction. Okay, since this is the optimal value, we are moving the correct direction. Okay, but if you are moving in this direction, where f of x plus eta d minus f of x is greater than 0, then that is not the optimal one. Okay, so we should always be moving in the our direction should be such that f of x plus eta d minus f dash of x is less than 0. Okay. So keep this in mind. We'll talk about that. We'll talk about the d in a bit. Okay.
Sir, this minus means f of x plus eta d minus f of x should be less than 0 only when we are moving from left to right, right?
No, that may not always be the case. In this particular scenario, we are moving from right to left. But let's say like I'll draw this diagram again. Let's say this is our optimal value. Okay, this is the minimum value, and then our x naught is here. Okay, our x is here. Okay. In this particular scenario, now I can't move to the left. I need to move to the right. Only if I move to the right, then only this is like x plus eta d realization. Okay. Only in this particular scenario, only if you move to the right, then only f of x plus eta d minus f of x will be less than 0. If you are on this side, then we need to move to the left side. But if you are on this side, you need to move to the right. Okay. It differs. It's not always that we need to move to the left or we need to move to the right. Okay. Is that your doubt? Right?
I was just asking that f of x plus eta d minus f of x is less than 0. In this case, I understood. But if we take x at the right side, then it is also true or not?
Yeah. That is true always. See, if you are here, and then this is let's say x, and then this is x plus eta d, right? Then in this particular scenario also f of x plus eta d minus f of x should be less than 0. Like only if you are doing that, then only we can say that we are moving in the correct direction, right? But if you are moving the opposite direction, or even in this case we are moving the opposite direction, then we cannot say that f of x plus eta d minus f of x is less than 0, right? Then that clearly means that we are not moving the optimal direction, right?
Okay, sir. Understood.
Okay. So now what we have is, we know that f of x plus eta d minus f dash of x should be less than 0. Okay. Then only we can say that we are moving the optimal direction, right? So basically, since we eliminated all these higher order terms, what will this f of x plus eta d minus f of x be? That will be eta d into f dash of x, right? Correct? Eta d into f dash of x. So basically, this eta d into f dash of x, it should be less than 0. Okay. Eta d into f dash of x should be less than 0. We know that eta should always be this positive. Okay. So which leaves us that d into f dash f should be less than 0. So for d into f dash f should be to be less than 0, we took this d value as minus f dash f x. Okay, we took the choice of this d as minus f dash f x. Okay, that is why initially we took that xt plus 1 equals to xt minus f dash f x. Okay. So only when we take that d as minus f dash f x, then we move in the right direction. There we explain it using the graph. Now we are explaining using the equation itself. Okay, clear? Is it clear? Okay, so this is when we are having one dimension, right? But let's say like we are having higher dimensions, then for you to find this f dash f x, obviously we cannot do f dash f x directly. There we can only do the partial derivative. Okay, partial derivative with respect to we will denote this as f dash of x or something, f dash of x or f dash of y, only if it is a function of x or y. Okay, but if it is a function of like more than one variable, in this particular scenario x1 x2, okay, we will be denoting this by partial derivative. Okay, this is that dou f by dou x1 or dou f by dou x2. Okay, clear what I'm talking about? Okay, here if you're doing it for the higher dimensions, what we call is, we call this as like gradient. For the single dimension, we call this as just like derivative. Okay, clear? Shall I move ahead?
Yes, sir, clear.
Yeah. Okay. So based on these values, we just use the same thing again. Okay, like f of x, like xt equals to xt plus 1 equals to xt minus f dash of eta into f dash of x. We use, right? The same thing we use for higher dimensions also. But the thing is, there that before xt was single dimension. Okay, but here xt will be a vector. Okay, xt will be a vector. Even this gradient also will be a vector. All right, clear what I'm talking about? Like in this particular scenario, we have this x1 x2, right? So let's say like I need to find xt plus 1. So xt plus 1 will be equals to xt that, let me not use this xt again because it will be confusing with respect to x1 x2. So I will use I will denote it at the top. Okay, xt plus 1. Okay, I will denote at the top. That means that we are finding the t plus 1 iteration value. Okay, so which will be equals to xt1 xt2, okay, plus gradient of f. Okay, so this gradient is nothing but actually minus dou f by dou x1 dou f by dou x2. Okay, so this is again a t. Okay. So this is now a two-dimensional vector. Similarly, you can do that for like n-dimensional vector like x1t, x2t, x3t, and so on. Okay. Minus beta into, since f dash of x is, so now the f dash of x, the gradient is here will be dou f by dou x1, dou f by dou x2, and so on, dou f by dou xn. Obviously at the t. Is this clear? For the higher dimensions, how do you find the t plus 1 the vector? Okay, clear? Okay. So in our graphs, like that cover example which we had, right? even there we have this higher dimensions, like we there that objective function, it is a function of x1, x and y, if you remember. Okay, that x and y. Okay, here they denoted that as x1, x2. Okay? But the main important takeaway is that like there we have like two variables, x and y. Okay, it's not just x. So the same thing which I mentioned. If you are using this gradient descent for the higher dimensions, then this will be vectors. Okay, but if you're just using for this normal one, then this will be the normal way which we had, xt plus b equals xt plus eta into minus f dash x. Okay, clear? Even the Taylor series also you could do it in the same way. For x plus eta d equals to for x plus eta, it will be d transpose. Okay, yeah, it will be d transpose into del f of x plus and so on. Okay, so if you look at it, x plus eta d is a vector, but f of x plus eta d, that is a scalar. Okay, f of x, f of something, that's going to be a scalar always. Okay, so since this f of x is a scalar, and this d transpose del f of x, that will be a scalar, because d will be of n cross d will be of n cross n, and then del f of x also will be of n cross 1. If you do this d transpose into del f of x, that will be 1 cross 1 vector, which is nothing but scalar. Okay, is it clear what I'm talking about? Del f of x is n cross 1, right? And d transpose will be of 1 cross n matrix. If you multiply both, then you'll be getting 1 cross 1, which is nothing but, which basically means it is single value scalar. Okay, clear? Clear? Continue.
Hello, sir.
Yeah.
Sir, sir, go to the slide again. So, sir, here in the graph, the above graph, yes, that's square. So, sir, what this directions implies here?
What direction?
The arrows. Yes. The arrows.
Here you're talking about which direction we should go from. Is it?
Yes. Yes.
Okay.
So, sir, draw some arrows here. Yes.
You want me to draw some arrows in there, like right direction, the right direction, wrong direction, that one?
No, sir. Draw some arrows here in this graph. So, what this implies?
You want to draw the arrows?
Points 30, 50, 40, 40, and 5, 2 vector points.
I did not get you. So we started from 5 to that's what you were talking about?
No, sir, the red arrow. Red arrow.
I don't know what you're referring to.
I am asking what this arrows means here.
What is arrow?
So in this diagram,
in this diagram.
The red arrows, what it implies?
What does this arrows imply?
Yes, sir.
Okay. So we are we are at this 5 2 initially. Okay. Here we are at 5 2. That is x1 x2, or you could call this x comma y. Our actual solution, our actual like target is 40 comma 40. 40 comma 40 because we want to minimize the distance between these two, right? This distance of x1 comma x2, that is x1 minus 40 whole square plus x2 minus 40 whole square, that should be minimized, right? For it to be minimized, we move closer to this 40 comma 40, right? So initially the direction from 5 comma 2 to 40 comma 40 will be in the direction pointed out, the red direction which is pointed, right? So that will be the good direction. Okay, that will be a good direction.
Yes.
And from 30 comma 40, like let's say like after some n iterations, you move to 30 comma 50, and then you are at 40 comma 40. Okay. Now you need to be moving in this red color direction, such that you'll be moving in the good direction. Okay, that's what it means.
Okay, sir.
They just denoting the same good direction, like the direction which we need to go move. Okay, but here we have two dimensions. unlike the previously where they are like single dimensional. Okay.
Okay, sir. Got it. Thanks.
So here it's the same thing. Like for the higher dimensions, we take this d as is minus del f of x. The reason is still the same, because when we take this d as minus gradient of f of x, if we do this d transpose into gradient of f of x, right? That is going to be minus mod of gradient of f of x whole square. Since this gradient of f of x whole square, that mod value will always be greater than or equal to 0. The minus of it will always be less than 0. Okay, so we will still be moving in the good direction. Okay, when we take this d as minus gradient of f of x, this for higher dimensions. Okay. So the part of like so we have this d transpose w. Let's say like okay. So here we have this vector w, right? W and w2. Okay. Here we have these two dimensions w and w2. Okay. We know that when you take a vector that is like perpendicular to it, right? Then like some vector d which is like perpendicular to it, then d transpose w, that's going to be equal to 0, right? Because they're like perpendicular. The dot product of two perpendicular vectors, that is 0, right? Okay, so d transpose w, that is 0. Okay, the right side of it, the yellow colored region is d transpose w greater than 0. Okay, the left side of it, that is a green colored region, that is where d transpose w is less than 0. Okay, that is where d transpose w is less than 0. And then our goal is to reduce this. Our goal is to have this d transpose w to be less than 0. Okay, for a vector of del f of x.
So why is it greater than 0 in this direction, less than 0 in this direction?
Why is this? Okay. What we are basically doing there is dot product, right? So we have this. Okay. I have a vector. Let's say w here. Okay. And what happens if I'm let's say I have another vector d here. I have d here, right? So what do you mean by this dot product? What do you mean by dot product? It is a projection of d on w, right? Correct? It is a projection of d in the direction of w. Am I correct? Hello. D dot w. D dot w. Okay. What is this mod w whole square? What is mod w whole square? That is nothing but w dot w, right?
Yeah.
Right? So w dot w is greater than 0. You all agree to this? W dot w is greater than 0.
If w is non-zero, yes.
Huh?
If w is non-zero, then it's greater than 0.
Yeah, w transpose. Yeah. W dot w is nothing but w transpose w, right? Which is nothing but greater than 0, right?
Yes.
Right? So what do you mean by w dot w, which is nothing but this one, no? When d is equal to w, that is, this is w and this is also d. When we have d and w both in the same direction, then d dot w is greater than 0, right? Since d is equal to w. Clear? No?
No, sir.
You didn't get it?
No.
So okay, when we're doing dot product of one vector onto other, right? One vector onto other, it is nothing but the projection of this vector on the other vector. Okay, like in this particular scenario, if I have d here, and W is pointing to this side. The projection of this on the direction of W, that will be the d dot W. Okay, that is the reason. If you have this D, if you have the D perpendicular to W, right? There is no projection of the projection of D onto W is nothing but a single point. Okay, that is why d dot W is equal to 0 when D is perpendicular to W. Okay, and this will be maximum. The projection of D onto W will be maximum when D is in the same direction of W and it is of same magnitude. Like let's say we have this D. Okay, the D is in the same direction and W is also in the same direction. Then the projection of D onto W, that will be the maximum. Still not clear?
Yes, sir.
Right. So for suppose let's say we have D here. We have D here, and then we are doing the projection of D onto W. We are doing projection of D onto W. The projection of D onto W will be in the opposite direction. Like in the opposite direction. Since D is pointing to this side, if we are doing the projection of D onto W, that is in the opposite direction. That is why all this area, like whichever vector you take this vector, anything, right? The projection of all these vectors, that is d dot W, is going to be less than 0. Okay? Exactly when they are perpendicular, since there is no projection, the d dot W is going to be equal to 0. And if you are moving in this place, if you are at this place, then the d dot W is going to be greater than 0.
And so like it is because D is negative, that's why it's less than 0 in this area, because of negative, D is negative, that's why D dot W is less than 0, right?
Like yeah, D is negative with respect to W. Yeah.
And also like you said D dot W is equal to 0, right? So in the opposite direction also it is D dot W equal to 0, right?
Right. Because you're talking about here, right? You're talking about here now.
Yes, sir.
Here and here. Yeah. Because in both the scenarios, the projection of this onto this is 0. This is like I'm moving in this direction, you are on this direction. The projection of this onto this is going to be just a single dot. Okay, right? And the length of that is nothing but 0, right?
So like the line and the left line, I mean perpendicular, like the top and the left line.
This one?
This and the left, yeah. This is perpendicular.
Yeah. This?
Yes, and the top one.
This one?
Yeah.
Okay.
So these are perpendicular, so this will be 0 as well. Even though.
So yeah. So this is nothing but minus W, right? This is nothing but minus W, and this you could assume like something else. Okay. Since this W is perpendicular to D, this also means that minus W is perpendicular to D. So the projection of D onto W is 0. Okay.
Yes.
Minus W is 0. Yeah, you're correct. Okay. Clear?
Yes, sir.
You could think of it in this way. Okay. The angle between these two vectors is let's assume like theta. Okay. Let's assume like theta. If the theta is let's say like less than 90, it could be clockwise or like anti-clockwise, it doesn't matter. Okay. If the theta is like less than 90. It is less than 180. Okay. If it is like less than 180, then theta is less than 90. Then we have that the projection of D onto W is greater than 0. Okay. If the theta is equal to 90, then they are perpendicular. Then the projection is equal to 0. Okay. Then D dot W is equal to 0. If the theta is greater than 90, like it could be like until 180. then d dot w is less than 0. Okay. So if you see here, this is w, and this is d. This is w. This is d, and here the theta is like less than 90. Okay. But if the d is if this is d, then this angle is greater than 90. Okay. Then d dot w will be less than 0. Okay. Clear?
Yes, sir.
Okay. Even if you take it in this direction also, this angle is going to be greater than 90. So that is why for all the vectors in the direction of like green, the theta will be greater than 90. So that's why the d transpose w is going to be less than 0, or the dot product of d and w is going to be less than 0. Okay. And in the yellow colored region, since the theta is like less than 90, okay, the d transpose w is going to be greater than 0. Okay. So and the greatness of this is of this minus del f of x is we are moving in the we are moving in the exact opposite direction. So we'll be going to that optimal value like quickly. Okay. It is the like you could say like the biggest negative value possible. Okay. Since we are moving like exactly 180 degree opposite. Okay. Clear?
Yes, sir.
So that's what they have explained here itself. I talked about this vectors, right? Vectors. For all these vectors, for all these green colored vectors, the theta is greater than 90. So that minus d the d transpose del f of x, that's going to be less than 0. But for d equals to minus del f of x, this is like the steepest descent which we have. Like from xt plus 1 now. For xt plus 1, that will be the steepest descent. For xt plus 1.
So I didn't get this one as well because I got the first one, but this is like derivative, like gradient. Like why is this here negative?
Why is this?
Like why is this negative here in this direction, positive in this direction, this delta fx?
Why is this steepest or like why is this negative?
Yeah, no, like why is it negative here and why is it positive in the right direction? Like
I was just talking about this. So this is the w. Now the w is del f of x. Okay. The opposite of it is going to be minus del f of x. No, the exact opposite direction. That's going to be minus del f of x, right?
That was a wpx, right?
Huh?
That was the dot product. This is the derivative gradient.
The gradient is also a vector, right?
Yes.
The gradient del f of x, I told that is nothing but x1, x2, and so on, right? That is nothing but a vector. No?
Yes, but it is a single vector. We're not multiplying or doing any dot product with anything.
If you're having n dimensions, you're talking about.
Here, like in this example, like I don't get why is it positive here.
You're talking about you're talking about del f of x, right? Del f of x is there, and then the opposite of it, the d is going to be minus del f of x.
Yes.
Okay. So the dot product of both of this, it's going to be negative. Okay. If you take any of these green colored vectors, the dot product of those green colored vectors with respect to this del f of x, that's going to be negative. It's the same as this, right? So confusion.
Yeah, because agreed.
Right. I was just talking about this now. See, for all these green colored vectors, with respect to del f of x vector, now the theta is greater than 90. To see.
So you have to like name this, like the line in red which is going down. We have to name it like v vector, and then we like multiply v with the gradient, and we get the same thing as above, right?
Sorry, I'm not
like,
getting.
You know the red line in the middle which is going down.
This one?
Yeah, we have to name. So if I name it vector v, for example,
Okay.
If I do v into this gradient f of x, then I get
0.
9. Yeah, so that's the same concept, right? Like
Yeah, it's the same
they
concept.
didn't name the vector here, so I got confused.
Okay. So like here Saur talked about like general vectors. So Saur applied that to this gradient f of x vector.
So this written is basically like d only. D in the above example. Yeah, okay, got it. Yeah.
So yeah, that is why when you take this GD, right, that is the steepest descent algorithm also they take. Okay, because they're taking the exact opposite direction to this del f of x. So that is the steepest descent. Okay, clear?
Yes, sir.
Yeah. So any other questions you have like in week 7? Okay. There are no other questions. I think Vishal or Jimmy can continue with week 8.
Yeah, I'll continue with week 8.
Thanks.
Yeah, thank you. Okay, so is my screen visible?
Yeah.
Yeah, so yeah, let's start. So in week 8, these were just yeah. So in week 8, these were the topics which was covered by the sir. Yeah, hello. Is someone saying anything? Okay, so yeah, let's start. So these were the topics which was covered in week 8. The first topic was constraint optimization. Then sir covered method of Lagrange multiplier, projected gradient descent. It was covered in a brief manner. So yeah, then introduction to convexity, properties of convex sets, convex function, and their properties. Okay, so yeah, I will just give the brief, quick recap of all the topics, and yeah, we will be able to cover the questions and all. Yeah, like that we will do. Okay, so yeah, in the constraint optimization, our target is to check whether the given x r satisfies the condition and is it indeed optimal or not. Okay, so to do that we have two conditions. First is whether the gx stars is less than equal to 0, and the other condition is no descent direction should be a feasible direction. Okay, to represent it in a mathematical form, we have del of f star equals minus lambda times del of gx star. Okay, if it is an inequality constraint, then lambda should be positive scalar, and if it is an equality constraint, then lambda can be a positive, negative, both. Okay, so yeah, so how we solve the problems? Okay, and this lambda term we call it as a Lagrange's multiplier, and this method is called as a method of Lagrange's multiplier. Okay, so what we do is the first step, what we do, like we just take the partial derivative of del f and del x, del z, and we just equate this, we just form this equation. Okay, so once we form this equation, and the second equation it comes from the constraint equation del z. Okay, using this one we get this equation like g of xy equals k. Okay, so by using these two equations we have to get the value of x, y, and lambda. Okay, once you got these three values, and then you can put in the for xy, and you see that whether it's a minimum value or maximum value. Okay, if it is a minimum value, then yeah, at that point the function is function is giving the minimum value. Okay, or if that the total value is maximum, then yeah, that point is a maxima, something like that.
A negative sign before lambda.
Yeah,
Shouldn't there be a negative sign before the lambda?
see, the sign of lambda doesn't it won't affect your x or y value. Okay, whatever the sign you will take, that will be automatically taken care of the equation. Okay, it is like x, y, z is there, no? You will see that if you take the lambda sign plus lambda or minus lambda, in both cases you will get the same answer for x, y, z. Okay, the thing is like yeah, you can say one thing. Yeah, if you, what will you do if I ask the value of lambda? Okay, so The thing is, see, if you will, I will just see, if in normal cases, if here I get the lambda value as, see, whether my this whatever I am annotating that is visible, no? Like whatever I am writing.
Yes, sir.
Yeah. Okay.
Yes, sir.
Yeah. So if lambda value is 5, let's say, okay, in this case you got, and if you use the lambda minus lambda sign here, no, in that case you will get a lambda equal to -5. Okay. And after that, yeah, x, y, z, del, z value, whatever is the value, that will be the same. Like in both cases, you will get the same value. You can check that. Okay. So your final answer won't change, but yeah, if I you can ask one question like, what if I will ask the lambda value? Okay. So just be assured that we won't ask the lambda value directly. Okay. If we ask, then we will ask the magnitude only. Otherwise, yeah, you can, if we ask the we ask the lambda value and we are giving, yeah, it is -5, then yes, you can challenge it. See, yeah, it can be 5 also, because it completely depends on like which type of initial assumption you take. Like, so in many places, people do like yeah, sometimes we take this minus lambda value and sometimes we take this plus. Okay, so that won't change your final answer. And I think, yes, sir has taken minus or plus. Hello?
I took minus.
Okay, okay, that's okay. You can solve using both. Okay.
And so, like, I have one doubt. Like, this equation, like lambda f equals to this. I didn't understand this equation. Why are they proportional? Like delta G and delta f. Yeah. Like, how is this?
So in the okay, you due to this not really, yeah. So in this one only, like in this one from here only, no, we just so this equation.
Yeah.
Del of f star.
The second line, even like why decent direction should not be feasible and why this equation holds.
Okay, okay. So you ask that. So the thing is, let's say at this point, again, I'll draw the same diagram with third draw. Okay, so this is your x star value. Okay, and this is your direction of x star. Okay, where it means that your function value is increasing in the direction. So obviously in this direction it will decrease. Okay, are you agree with me?
Yes, sir.
Yeah. So in this direction your function will decrease. Okay, so this is your constraint. It means that you are stopping, and just we will plot this one also like g of x star. Okay, let's see, this is your x star. So let's say this is somewhere this is your direction of g of x star. Okay, actually del of g of x star, because so you know what this del function does. Like this del function says like at which direction your x star value will increase the most. Okay, so it is like that. So in this direction your del of f of x star value will increase the most. So this is giving you that direction. So like that. So what we are saying is, if
one doubt, sir, what is x star, sir? What does it denote?
X star is a value, like I am giving some value to you and I am claiming that at that point the function is giving the minimum value.
Okay, sir. Thank you, sir.
Okay,
Thank you, sir.
that you can say that is a critical point, in other words. Okay, at whatever point you want to check that. So what here it is happening is, so your del of up star is there, and so del of gx star is giving you this direction. Okay, I think yeah, should be better if I draw it in here. Okay, because I can use multiple colors. Del of up. Okay, and the thing is, okay, let's take this direction del of g of x star. So so if del of x star is this one, so it will be negative in this direction. Okay, in this direction d transpose del of up star will be less than 0. What does it mean is, like if we will move in this direction, like let's say this one is this x star value is your 5. Okay. So if you will take that x star value and let's say, hello.
See the drawing.
Yeah, sorry.
You cannot see your writing.
Okay. You can't see. One, let me. For us.
Sir, I have a question.
Yeah.
Sir, I just joined back in the live, so I don't know if we already covered it or not. So for conditions needed to be satisfied, g of x star is less than or equal to 0. We are using minus lambda, right?
Minus lambda. Okay. Yeah.
Yeah. So
yeah.
G of x less than or equal to 0. When
Sorry?
g of x is equal to 0, is it or
I think your voice is breaking. Is it for me or for everyone else?
No, sir, his voice is breaking.
Okay.
Sir, may I ask another question, sir?
I think I should complete first. Okay, just ask. Maybe.
Sir, for which configuration Lagrange multiplier is used? Whether it is for equality constraint or
Equality constraint.
Okay, sir.
Okay, so that's why our lambda can be positive or negative both. Okay, so yeah. This diagram, I think, I should pick because the sir has explained the same thing. So I think I should try it in some different manner. Say, let's say your x star is 5. Okay, let's take the practical example. What is we are saying? X star equals 5. That is a point, and your fx star, your function is, let's say, something 5x square plus 3. Okay, and your g of x is something, let's say, okay, anything x equal to 5. Okay, so what I'm saying here is you have to get the sum at this extra. I'm just don't interpret like it's a correct equation, but just the thing, whatever the I just try to represent it with the number. So just think like x. I'm giving you the value of x star equal to 5. So you have to check whether it's your minima point or not. So for that, what you will do first, you will check whether it is satisfying your constraint equation or not. Okay, so the first equation was coming from this one, like g of x equal like x equal to 5, it is given some or whatever will be the equation. The first equation comes from there. Then second equation, what I am saying is, if this is your gradient action, if no, your gradient action is not your constraint. I should represent it here only. So let's say this is your constraint part, okay, or you should think like x is less than 5. Okay, just try to draw it with the graphs only. Or we are taking that x is less than, or here just draw. Okay, so this is your constraint part. I mean, what this equation is saying, that I have to take any value less than this one. Okay, and our function is something in this shape, let's say. Okay, for example, I'm taking it. Okay, so what it is saying, that the second statement, like no descent action should be feasible action. So in when it will happen, the thing is, like if you take some this point, okay, after this point, even the function if you take this one, these values, at these values the function, see, these are the feasible action, but still it is not your decent action, because your after this your function is not getting satisfied below this one. So it is a something, you can say that it is a critical point. After that, you may have the feasible action, but it won't be a decent action, means your value of the function won't decrease. It is just a simple term. I mean, function is saying that you have that at that point your function is giving the minimum value. Are you getting my point, or something I should explain more?
Oh, sir.
Okay, so in this case, just take it in a simple manner. This sentence is saying you are getting that point of function. Okay, this is your function, and you are getting that point of function. After that, even even your other values are feasible. I mean, in the feasible, to say this one was your x equal to 5 only, x equal to 5 at this point, and after this, if I will take any x values, let's say x equal to 6, it is still in your feasible direction. Okay, still it's in your feasible direction, but it is not reducing your function value. So again, then I can use this search graph only. So what was it was like a del of x star is this direction. So your direction in this direction, your function value will decrease. Okay, your function value in this direction, it will decrease, and del of gx star is this one. So in this direction, this is your since the gx was also less than equal to 0, so in this direction your gx will decrease. Okay, so you have to reach at some point where you it's feasible also, but still your function is not decreasing in that direction. Okay, and you have to reach at that point, like after which, if you are this is the after which your function is if you will move in that direction, either your function is not descending or it's not feasible. So this is it is something like that critical point x star.
Like, so we're at the perfect point. We're at the point where it is the most minimum, and from there we're moving, and wherever we move, it will not be feasible, basically, right?
Yeah, just repeat it what you said.
So we're already on the optimal point where the value is minimum.
Yes.
But from there, we're saying that if we move in any direction from there, then it will not be feasible because it will always be larger than the point we're at.
Yeah, it is like that only, exactly. But just one more case is either it won't descend in the feasible direction. If the value is decreasing, then it won't be a feasible direction. It is like that.
What does decent direction here mean?
Yeah.
What does decent direction here mean? Because it can be in any direction basically. So why only just decent direction? What does decent direction mean? Basically?
Decent direction is those direction in which the function will decrease. Like if at x equal to 5, you are getting function value as.
But there's decent direction because it's not reducing anywhere else. Like it will be larger than that optimal value, so it's not decreasing any. So it won't be. There's no decent direction basically, right?
Sorry, just speak it again. I think
there's no decent direction here because we're already at the minimum point, right? So,
yeah, that here. Just complete.
So there's no minimum point. So value is not decreasing anywhere. We're at the minimum point. So there's no decent direction. Like
yeah. After this, there is no decent direction. Yeah, exactly. Like this is your minimum point. That's why it is your optimal point here. But there can be some cases. One case you got exactly. Yeah, because here we don't have any further decent action. Okay, so that is correct for this case. But and one more case can happen, like there would be some decent action, but let's say here it is like that. Okay, but your constraint equation is like this. Like this is your let's say there you have some constraint equation, and it is saying that your value should be more than this one. Like okay, constraint equation is something like it is saying that your value should be, your x value should be more than this one. Okay, above this line, your x value should be above this line. In that case, just think about this point. Okay.
right.
Yeah, in this case, this will be your optimal point, this one, because after this, if you will move in this one, this is like it is a decent action, but you can't reach at this point because it's not feasible action. Okay, these are not feasible points. So yeah, these two cases can happen. In one cases, yeah, there may be it is a decent point, and yeah, it is the minimum point, optimal point, and you have decent action, you have feasible action, but yeah, your value is not decreasing. your function value is not decreasing. And in this case, yes, your function value can decrease, but it's not a feasible direction. Okay.
Yes, sir. Yeah.
Yeah.
And so like
Yeah.
delta f equals minus lambda, like why does it hold?
Yeah, sorry, this minus
Delta f equals this lambda, this why the proportional, like how did this equation come? Like,
this equation, how does it came like that, you are saying?
geometrically, yeah, like I want to understand, like why does it hold true?
Okay, so in that case, see what is happening is in this equation only, just interpret from this diagram only. So in what cases you won't get any common value, any common like these two directions won't be will be exactly opposite. It can happen only in one case, like if this is your del of f star, so this is will be your in this direction it will be d transpose del of x star would be less than 0. Okay, and if your if your del of gx star will be in this direction, in this cases only your d transpose del of gx star will be less than 0. See, in this case only, there is no, this is your descent direction, this is your feasible direction. So this, your sentence is saying no descent direction should be feasible direction. In this is only the case where it can happen, okay? Or maybe, yeah, if we talk in terms of inequality constraint, okay? So both of this direction should be opposite. In that case only it can happen. So we are just representing it in the functional term. So del of x star should be multiple of del of g star. Just the lambda value can change. Okay, means just the magnitude can change, but yeah, direction should be same. So that is what is represented in that term.
Like why does the direction like need to be opposite? Sorry, sir, like I didn't get that.
Yeah, which one? What?
Like you draw like delta g like opposite of delta f, right? Like
Yeah.
by
Yeah, sorry, why? Like because in this case only these two like these two direction will be there won't be any common point in these two. Like this is your feasible direction, this is your descent direction, this is your feasible direction. There in this case only we won't get any common point. Okay, so if we won't get any point, see first sentence you got this sentence, no, like no descent direction should be a feasible direction.
Yes, sir.
So you take any direction of this del of x star, you will get some common point. Okay, it is nothing but just a perpendicular of this line. No, you just draw anything. Okay, any direction. This is your del of x star. So this is your descent direction, and you draw anything, any line. If you so let's say if you take this line as del of gx star. Okay, del of gx star. In this case, your feasible direction will be this. So you got some common point. No, you have to draw in such a manner that you don't get any common point. So that can be possible only in this case. Okay, like if both are is opposite direction. Okay, or in terms of inequality constraint, it can be parallel also. So in that case, because it is equal to 0. Okay, but in terms of inequality constraint, yeah, either it should be in exactly in opposite direction, or yeah, in that equality constraint it is equal to 0. So yeah, it can be parallel also.
So in the diagram you draw visible direction is like below. It shouldn't be above visible direction in the left diagram.
Sorry, just say.
Side of the page you draw a diagram, right? So you you said that visible direction would be below. Wouldn't it be above the visible direction?
See, the feasible direction equation was something like g of x star should be less than equal to 0. It was equation was something like this.
Right, yes, sir.
Yeah.
Okay.
Okay, yeah. So yeah, we are clear with this point. Okay. So let's move to the. So yeah, these were the steps to solve and you can try this question. Yeah. So the next topic was the project gradient descent. Obviously, we won't ask any question because sir has covered in just like 1 or 2 steps. It is Nothing but I'll just like otherwise I'll just try to explain visually. Okay, so what we are doing, it is just nothing but just a gradient descent plus projection. It is just like all these steps are as same as a gradient descent, but it's just like once we are going out of that set, like that constraint set, then we are just projecting it. That is the just extra step in this one. Okay, so yeah, just I'll try to explain it in this example only. Like, see, initially your, let's say, x0 point was there. Okay, if it is here, so what point will be the what would be the distance of this point from its from the closest point, which is belongs to this set? Are you getting my question? I'm saying this is your x0 point. Okay, so you can take any point from this set, and what would be the least distance of that point from this point, x0 point? Okay, let's break it into two questions. So which point is the closest point from this point? Okay, let's say you can take any point from this Q set which is closest to this point. So which point will be the closest point from this point? That is my question, first question.
Although like we cannot take inside like on this.
Any point in this set, in this Q1. You can take any point in this Q set, okay? And you have to tell the which point is the closest to this one.
X0 will be closest. Like,
yeah, exactly. This point is the closest point with its, it will be with itself only. Like x0 is the closest point with itself. Okay, so the distance between both points are what would be the distance? That would be, I mean, I'm saying that x0 is closest with x0. Okay, and distance between both points is will be 0. Yeah, exactly, that is what I was asking. Okay, so that is 0. So this equation will give you the 0 only. Okay, at x equal to, you have to put just x0 only. So like that only, like this is your Q is your constraint set. So when you are inside this set, you don't have to do this projection part. Okay, you don't have to use this equation because it will give you the 0 only. So you don't have to project it. Once you go out of this point, okay, out of this set, constraint set, okay, for example, here we go, reach at this point x0. Now your x0 is out of this set. Okay, so in that case you have to project it inside of. Okay, in that case this equation will work. This equation will help you to project your point. Okay, so in that case what we do, like you have to get the closest point of which belongs to this set, and it is closest to this one point. Okay, so you will just start drawing this Euclidean L2 ball. Okay, so you will draw one ball, and at the one point you will reach at this point. Okay, like this is the iteration. You basically in the iteration you do this only. So you will reach at this point. Okay, so this will be your closest. Will be your point which belongs to this Q set, and still it's closest to this your x0 value. Okay, so basically you do this only. Like so you will project this x0 to y point. Okay, so it works like that only. So if you got this, that's okay. Otherwise also, like it was just
here projection is like very different. Like here we do it by drawing balls around the point, right?
Yeah, the thing is, yeah, see, L2 ball is nothing but your Euclidean distance. So that is this equation showing, no, that norm. Okay, so it is like that. So that's why I'm saying, yeah, it is just a L2 ball, norm balls, something like this is just a Euclidean distance format, no? X1 minus x2 square, something like that. That's y2 minus y1 square. It is nothing but representing that all the distance on this point are same from this point, because all the radius is same, no? I mean, all the point which are on this red line is equidistant from this point. It's just just a mathematical term we are using, nothing else, but yeah, the same concept behind this is same. Okay, so yeah, let's move to this one. So the next topic was convexity. So obviously graphically convexity is a set, we have given some set, so how we will check it is convex or not? So it is just simple that just try to draw a line which is in this set, the end point of the line is in this set, And if the if that complete line is in this set, no, then yeah, we can say that it is a convex set. And if the line doesn't belongs to this set, then yeah, it won't be a convex set. Okay, so that is written here. Graphically, a set S is a convex if we take any 2 points from the set, and when we draw a line segment connecting them is also in that set. If it is not possible, then obviously your set is not a convex set. Okay, and yeah, the same thing is written in this equation format, because yeah, so like that, I think we have already did enough about this one. So yeah, convex L is nothing but just an intersection of your convex set. Okay, so yeah, convex, it is just your intersection of your convex set. Multiple, if you have multiple convex sets, yeah, so then it's an intersection of. So the next term was like convex function. What is convex function? It is just simply there was more than one definition for convex function. Like we can say that if a function is a convex function, if its epigraph is a convex set, or if it's always eigenvalues are non-negative, or it's a positive semi-definite. Both the equations, both the sentence is saying the same thing. They are saying that yeah, the function should be positive semi-definite. If your function is positive semi-definite, then it is your convex function. Okay, because for positive semi-definite only, the eigenvalue will be greater than equal to 0. So yeah, the same thing these two sentences are saying. Okay, and yeah, let's. So is it over? Okay, yeah, it's over. So yeah, these things were there. So yeah, one question was that like when to how to decide like whether a function is positive, semi-definite, definite, or something like that. Let's take, okay, just I think yeah. So let's take a function, okay? Just 3 cross 3 fx equal actually. Okay, let's take this function. So we have to do like whether you have to check it's a positive semi-definite, or if it is positive semi-definite, then we can say it is convex function. Am I right? Hello? Hello?
Yes,
Yeah, Jimmy.
Yeah.
Yeah,
Okay.
you can go on.
Yeah. So we have to say that whether it's a positive convex function or not. So we can decide by just checking that whether it's a positive semi-definite or not. To do that, we have to convert it into the Hessian form. Okay. So we have to convert it in Hessian form. It is nothing but just your first is your f of xx, second will be your f of xy. This what we use. You have seen for 2x, 2 cross 2. For the 3x, it will be like this, f of xz. Now it will be f of yx, f of zx. Okay, f of yy, f of zz. Okay, and yeah, f of yz, f of zy. Something like that. You can see this will be your equation for your 3 cross 3 form. Okay, and if you have 4 like 4, then yeah, you can write that one also here. Something like that. You can make that Hessian matrix. Okay, and now you know that like it's like it is nothing but just a representation of dou square f by dou x square. So like that you can differentiate and you can create that matrix. You will get some numbers here and here and here. Okay, and as Vishal said, like the most easiest format is this one only. Like you just calculate this one, you just check first. This one is this one is greater than equal to 0. Okay, and if then again calculate this one, like AC minus b square whether this one is determinant is greater than 0, then calculate the determinant of 3 cross 3 matrix. If that is also like whatever it will be the equation, A into BC, something like that. So if this is also greater than 0, in that case you can say, yeah, it's a positive semi-definite, a positive definite. Okay, if all are greater than 0, or other method is there, like you can calculate all the eigenvalues. Okay, or one
So
thing.
all the three determinants we need to calculate, or whenever we get the greater than 0, then we have to stop.
Yeah, sorry.
I mean, all the determinant values we have to calculate, or whenever we get the determinant value is greater than 0, we can
You have to
stop.
calculate all the determinant. You have to calculate all the determinant for 3 cross 3. Yeah, you for 3 cross 3 you have to calculate all the determinant. The same thing we are doing. No, for a 2 by 2, we are seeing what we are seeing. First we check this one, A should be greater than the. Then again check with this one, like AD minus BC. Obviously these values were equal, so it is like, yeah, we were representing something like that. So it was like AC minus B square should be greater than 0. So we are doing that only.
Okay, same thing.
Yeah. So this is what we were doing. And one thing was like whether it can be greater than it will be it have to be greater than 0. It can't be greater than equal to 0. Just take some value here which is 0. Okay, because that is what extra term is coming. In that case, what will happen? Like it is V, and this value is C. In this case, if you see if it is 0, then it is your determinant value is minus B square. So obviously your determinant value is less than 0. So in that or any cases you can take one, because these both value will be same. So obviously the product of these two will be positive only. So in if this is 0, then in every case you will get the determinant less than 0 only. Okay, so yeah, that condition won't satisfy. So that's why we are saying that this value will be always greater than 0. It can't be greater than equal to 0.
Yeah, got it.
Yeah, so yeah, that is what the okay. So yeah, that is all about the wicket. So anyone have any specific doubt?
So
They can ask.
this holds that means it is positive definite, not positive semi-definite.
See, positive definite or positive semi-definite, we have the conditions. I mean,
Maybe any like from there to
in both cases, the thing is this A value should be greater than 0. Okay, you can it will depend like other matrix. C, it is like if you are saying for 3 cross 3, this value will be 100% positive. Okay, now if you get this AD minus AC minus B square greater than 0 or greater than equal to 0. Okay, or the whole 3 cross 3 matrix determinant greater than 0 or greater than equal to 0. You are getting my point. It means that you got the first determinant, you got greater than 0. It has to be greater than 0. Okay, then if you are doing for the 2 cross 2 matrix, if it is also greater than 0, and 3 cross 3 matrix, its determinant also greater than 0. In that case, you are saying positive definite. And if any matrix you got for, let's say for 2 cross 2, you got the value as equal to 0. Okay, so in that case, you can say positive semi-definite. It means for any value you are for any determinant you are getting 0, then in that case it will be a semi-definite. And if all the values are exactly positive, then it's a definite, positive definite.
So for convex, what should hold, positive semi-definite or positive definite?
Yeah, sorry, just for convex function it should be positive semi-definite.
Not positive definite.
No. Positive definite is already a subset of positive semi-definite. So if it is a positive definite, then also it will be equation will be it will be a convex function. And if it is a positive semi-definite, then also it will be a convex function only.
Positive or semi-positive, anything can be there, right?
Yeah.
Okay.
And the thing is, what happens is, in case of positive semi-definite, let's say this is your function. Okay, this is your real function. So and just try to think it in 3D format. So its shape is something like this one. Okay, just think like in the 3D space, its value is decreasing. So what positive semi-definite is saying that this point is minima at least in one axis. Okay, and if it is a positive definite, then we are saying that it is 100% minima in all the axes. It is like that. That is the word positive definite and positive semi-definite word says. Positive definite means this point is minima in all the directions, and positive semi-definite is saying that that point is minima at least in one direction. Okay.
at least in one direction meaning?
It means that it may be like in this x-axis. See, here only I was saying this is drawn in x and y-axis. Okay, so in this one, for this one, it is a minima point. Okay, but let's say if we are drawing it in z-axis, it is decreasing. Still, it will decrease. Something like this kind of shape I'm saying.
Like a saddle point. Like a saddle point, like it increases.
Yeah, like saddle point, or maybe that is what you can say. Means in that axis, one axis, it can happen like we can, that value can decrease. Okay. See, in that axis, the value is still decreasing. Are you getting?
Yes, sir.
Yeah, that is what this point says.
So
for the saddle points, it will be at the 0, 0.
In this case, saddle point will be at. Saddle point is nothing but the point we can't say that whether it will increase or decrease, something like that. Okay, so yeah. Just take it this one only, like in the positive definite, just like you are 100% sure it is a minima. In any direction you will calculate, it's a minima point. And obviously max global minima. That is what the convexity convex function says. Like if convex function is like local minima is a global minima. In that case only, like it's a convex function. So 3 terms we said. First we said like whether why I mean just try to briefly discuss that. First we got some equation, and our issue was to get to know whether it's a we have to know the optimum point. So for that the matrix we got that gradient descent method, okay, to get the optima. Okay, then in the second case what we said, like we put some conditions, like that equation, in that equation we put some conditions. So in that case, if that is a simple form, then you can use the Lagrange's multiplier. Okay, so your gradient descent helped you to solve an unconstrained problem. Okay, unconstrained issue. Then you got the Lagrange's multiplier, where the constraint, where the method is, where the equations are constrained, but still it's an analytical method. Okay. Lagrangian multiplier method. Okay, so for the constraint equation you got this one, and then the third came. This one was a completely analytical method, so obviously you can't apply it everywhere. Okay, so then next came projected gradient descent. Okay, so like that you increased. So then we came to some terminology, like we wanted to know whether it's for that equation we will get the global minima or not. Okay, so in that case we said whether just check whether it's a convex function or not. Convex function or not. Okay, so for that only, like for that we check the convexity, and convexity from that term we wanted to know what is the domain of that function. For the domain, the domain of that function is a convex set. Okay, from there that term convex set came, and this your convex function came, and yeah, when you came to this point like convex function, then you got to know that whether it's that local minima is a global minima or not. So did you got why I said like how all these things are connected, like that convex function came and then convex function after that, and all these things we talk in that covariance matrix. And two things, like you would be knowing that why you said why introduce positive definite, positive semi-definite terms in that PCA, because in that PCA when we draw that covariance matrix, it is also symmetric. No, it is also symmetric. So in that we just denote that whether it's matrix a positive definite, positive semi-definite or not, something like that. Okay, so yeah, that's all about this week, this week 8. So if you have still any doubt, you can ask now, or maybe yeah, discourse is open. Hello. So we started with I think 190 people. Now how many people are left? Yeah, 37 people. I must say, yeah, you people have
Actually, from from the principal component analysis, what kind of questions might come? I mean, in what level we can do the calculations?
Yeah, I think Vishal can say that more in more clarity, but obviously the questions would be very simple, like because I think mostly would be around positive, definite, positive, semi-definite, and few questions can be like, yeah, to just the matrix format and just do the transposition. Vishal, are you there?
Yeah.
Yeah, you
So
can.
the question won't be that difficult, like from the calculation point of view, right? So
Yeah,
because
right,
we can't give you the question that is like very lengthy in calculation part, right? So the
Even
question
for
would be
the
pretty
SVD
simple.
also, the calculations are pretty lengthy.
Yeah, the calculation part won't be that difficult. Mostly the conceptual questions will be there. Yeah. So you won't face that much problem in calculating. The calculation part you won't face much problem.
Actually, it's difficult to create questions like questions, easy questions from that topic. Like whether it will be either like descriptive type. So if it would be a like a theory type exam, then obviously a difficult question can be made from these topics. But yeah, here since it's a MCQ type, so obviously we will try to ask you questions in MCQ manner only. So obviously calculation will be lesser. Yeah.
So what I'll say, you can just practice all the graded assignment, practice assignment from 5th to 8th week, and 1 to 4th week,
Because
you can just
I'm asking as there is no mock test, so that's why I'm asking this.
yeah. So mock we are not providing this time. Like many of the courses you would not have got this time the mock.
Right.
Yeah, and the diploma courses. So we are not providing. But yeah, the question would be pretty simple. I've seen the questions, or the questions are pretty simple from week 5, 6, 7, 8. All those questions are not that difficult. The calculation part is also simple. It's just have to, what I can say, practice the practice assignment and graded assignment once again. And that would be more than enough, like from now. And yeah. Yeah,
Sir,
Jimmy, you want to add?
Yeah, the same thing. Like if you have the good command on graded and practice question, no, you will be able to clear like at least week 6 or week 8. Yeah, it's easy question only this time.
Sir, one question from week 5, that is a practice assignment, question number 17. So those points are like vectors are in decimal points. So how to guess it? I mean, I'm not getting, like I'm getting wrong basically.
So which question you're talking about?
Week 5 practice assignment, question number 17. 1717. SVD of a matrix.
Okay, you won't get those kinds of questions in the quiz, so you need not worry about it.
Okay, sure. Thank you.
Sir, I have a question from SVD too.
Yeah.
So sir, I was solving this solve with instructor session last question of SVD. A was given 1, 2, 3, 6. So I found V and sigma, but when I tried to find U, I got only one of the column matrix and in the answers you guys got both column matrices.
Yeah, see, if you get one of the one column, so what you're trying to say is you got one eigenvector, right?
Yes, sir.
So if you get one eigenvector, since that is a 2 cross 2 matrix, right? The other way, the other eigenvector, it should be orthogonal to this particular eigenvector, right? So that's a property of this unitary matrix now. So based on that, you can get the other eigenvector too. Okay.
Okay, sir. Thank you so much.
Yeah.
Sir, I have a question. When it comes to when we're talking about week 6, the most important part of week 6 is PCA, right? Positive definite is the basic stuff, and then we move on to PCA. So the whole process of PCA is pretty detailed, and dare I say it's a relatively lengthy one. So should we expect questions of around 3 to 4 or say 4, 5, 6 questions on a particular PCA equation, PCA problem, in various levels of solving the question? I mean, I hope I'm able to make myself clear.
Yeah.
Like it's a pretty detailed process, right? I mean,
yeah. So see,
needs to be done.
In the lectures, like sir has explained everything, like all the, what you can say, the procedural part, he's explained everything. So the thing is, you should be able to know the final thing, like And basic steps, like if you have to convert, like if you have to get the like we have done in the solve within Spectral also, right? So there are some questions that you can practice, like how to calculate the projection of any data and all, data sets, data points and all.
Yeah.
Those things you should be able to know. And if there are some conceptual question with like for statement and all, so you should be able to like.
No, that's not my question. I mean,
Yeah, I am getting your question. You are asking if like any elaborative question can be asked or not. Like,
no, it's not about elaborative question. I mean, PCA is a very long process, right? There are many steps involving PCA. So I mean, ideally putting it into only one question of about 3, 5, even 10 marks would be a bit.
No, there won't be any questions like that. If I'm asking 5 questions, all those 5 questions will be separate. Okay. If I'm asking like,
I mean, one PCA problem and 5 stepwise questions related to the steps.
If there are some questions on the PCA, so all those 5 steps
right?
will be consisting in a form of questions, and all those 5 questions will be consisting of some mark. So you won't face like I'm giving you some data set, I'm directly asking you to calculate the reconstruction error. I won't ask you like
that's going to be very unfair.
That is what I told you. It will take again.
Yeah, because sometimes if we get first step wrong, everything will get wrong.
Everything will be
it's a big
gone
loss.
completely.
Same thing happened. I will tell you that for MLP people, like that OP examiner, people if just think like 16 marks will be gone. Like for starting step, like preparation step, people have done wrong. And yeah, like next 60 marks was dependent on these things only. Like all the So this time we calculated the marks manually, but yeah, that I saw that.
And sir, one question, like, can we expect some MCQs this time in exam?
Most of the questions will be MCQ this time.
Okay. Because
like not most like
probability of getting,
right?
probability of getting is 0.
60% of the question will be, I guess, MCQ, right? This time.
Okay, and sir, will that include theory as well, or only the numericals?
Some numerical, some theoretical also. Like 1 or 2 can be theory based and all.
So,
okay.
Yeah.
Okay, sure.
You mean 60% will be numerical? What will be the other 40%?
Numerical answer based. Like you have to write the answer.
Like it will be theory.
NAT.
He was saying, whether it's I think Vishal saying that 60% question will be a MCQ type and 40% will be an NAT type. I think.
Okay.
That is what I was telling. MCQ means like you'll be having 4 options. Out of that, maybe 1 is correct or maybe 2 is correct, and there can be 40 or 50. Like half of the NAT question would be lesser this time. Like last time, somebody was saying. Last time, most of the questions, I guess all the questions were NIT, so that was pretty difficult.
Just wanted to confirm one thing. Actually, I saw this live session, so I watched it on YouTube earlier because I missed some part. So I saw that when you were teaching about positive definiteness, so you told about that we have to see the first value and then we have to see that we have to check for the whole table matrix. We have to go diagonally, and whether if all 3 values are positive, then we can confirm it as a positive.
Not diagonal value. I was telling
the first value, but checking the positiveness of like taking a graph in the diagonal form.
Okay, so see if you are having matrix, right? If you have been given the matrices, so if you have been asked regarding the positive definiteness of the matrix, okay, then what you will do, you'll just calculate, you'll just see the first pivot value, first pivot you are getting, right? The A1, okay. Then the leading 2, like 2 cross 2, see the 2 cross 2 matrix, then calculate the determinant of that 2.
Okay. So like all 3 should be positive.
Yeah. You have, if that is of 3 cross 3, then you have to check for all the 3.
And you have to there were three rules that were written by you, 1, 2, and 3. So what was that for?
1, 2. Wait,
follow like XT, AX.
AX. I'll share the screen once again. Okay. What is that? Yeah. So where?
It's in the yes, sir. The green part, the green.
Okay, this one. This see this. There are mainly what you can say 2 or 3 methods, and all of these are necessary and sufficient by itself. Like, well, if you are able to, what you can say, if you are able to prove the first one itself,
then you are very much even the first condition is very much sufficient to say that this positive matrix is a positive definite. Okay, so if you are calculating all the lambdas value, all the eigenvalues, and all the eigenvalues are positive, right? So you can say that this is a positive definite. Or you can say if you are calculating the pivot values I've just written like pivot values you have to calculate though like what I've told now a1 and then calculate the determinant for 2 cross 2 then calculate the
We
determinant
can
for
do any of these three, any one of these three.
any of the three is correct. Like I told you, it's all are sufficient. Like if you are able to do for the one, that is more than sufficient to prove that it is a positive definite.
Okay.
Yeah.
And sir, regarding the PCA that you were telling, other than finding the PCA value like reconstruction error and the PCA value, like is that the only numerical that we can be asked from week 7, like for the PCA part?
Yeah, there can be numerical, like you have to calculate the transform data set or the reconstruction error, or this sort of questions can be asked. Like if I'll ask you a difficult one, that will become very difficult to solve it manually, right?
So which one?
If I'll ask you to convert 5D into 2D, then it will become very difficult to calculate manually, right?
Yes.
That's why we can't ask those questions.
Sir, I had a general outside question. I saw that we actually reduce the variance and we want a low bias and a low variance in our data.
Yeah. No, see, generally you'd have read in stats 2 also. Generally, the bias plus variance is constant, right?
Yeah.
Bias square plus variance is constant for any graph plot, right?
Yeah.
So what do we generally do in any of the cases? Like it's not for the PC and all. Any of the cases, what do you generally do? You should be having any algorithm which generally consists of lower bias and such like you can't be having algorithm with the more variance and less bias. Okay, see, b plus b is constant, b square plus b is constant. So what you can do, you should be having a appropriate value of b and v both, such that you should get a good algorithm. That is what
like it was recommended about overfitting and underfitting.
So it depends on overfitting and underfitting also. So if you are having more bias, then it will go inside, it will overfit, right?
But sir, when you were telling about PCA, you were telling that if a feature is having a lot of high variance, then we have to take that feature into account. So like, is more variance an important part or is that a negative part?
See, I got your point. I think
No. Yeah, you are getting a totally different thing. I was telling about the different part, and you are getting the different part. You are talking about some other sort of things. I was telling you have to get the direction where the variance is maximum, and that is a bit difficult, different part. That is what that you are talking about, bias and variance. That is a different thing, and here we are talking about a different thing.
Okay, got it.
Yeah.
So in that variance, what you are talking about that, no, in that underfitting, overfitting, in that case, that variance is saying about the error which we are getting like after it,
that is
like,
about the error.
Yeah. And here this variance you can think at just spread of the data. You have to draw axis in such a manner that you are able to cover the maximum data. It is like that. You can here in PCA just replace that word if you are getting confused with that word spread, like spread of the data. Okay. Although in both cases the variance is different. Here you are just trying to cover the maximum data points, okay, by drawing that line, and there it was variance was about if you are creating different models and which model is giving you the lesser variance means giving you the lesser error, something like that. So yeah, I think there was a post, like I think I have written like long back a post related to this one only, like someone has asked this topic only, like here we are talking about decreasing the variance, and because the higher variance will do that overfitting, like that. There is a post, you can go through that.
Okay. Yeah, then.
Sir, which are the weeks we should concentrate, sir? 5 to 8. I
Yeah,
mean,
5 to 8.
okay.
Actually, you can expect more than 90%, I would say. As you said, like hardly 1 or 2 questions you can think from those weeks.
Oh, okay, sir. Thank you, sir.
Okay, then I guess we
Hi,
have
sir.
come.
So from 5 to 8, what topics we should focus on? From which we
Like,
can expect the questions and we can brush up and practice more.
okay, Jimmy, will you take this?
Week wise, I mean week 5, then week 6 kind of. So that would
Yeah,
be
sorry.
really
Just repeat the question.
Important
yeah. So
topics is
week
asked.
wise, what are the important topics we should focus on?
In week 5, I think Ram can say more about that week 5.
So in week 5, you can concentrate more on the SPD part and the finding the eigenvectors. Okay, eigenvectors. So the other part will be this that if a matrix is summation, right, that unitary, the diagonalization also, if you could look at it, okay, the properties of it, if you could look at it, that will be sufficient. And I'll talk about week 7.
Permission?
Huh?
Properties of
Diagonalization. Yeah, the diagonalization of the Summation matrix, you could look at it too. Okay, not the like complete calculations part of it, but at least the what is it, the properties. Okay, at least the properties are not, and like how you do it, that will be good enough. If you know how to do it, then that will be good enough. Okay, and for week 7.
Theorem and all, how to do the diagonalizable, how to prove the Hermitian matrix diagonalizable, that is the one?
Not the proofs and all, not the proofs and all. Proofs and all, we can't be asking it, right? You won't be asking any proofs and all. Okay. And for week 7, you could look at the normal gradient descent algorithm and the iterative process, right? To get to the solution, you could look at it and finding the maximum, like how maximum or minimum. How do you do it? Normally, like using f dash of x, right? You could just look at those. Like for week 7, I think it's going to be easier, I guess. There's nothing more than that to it.
So like normal graded, iterative process and maxima and minima from week 7.
Yeah.
Okay. And 6 and 8?
Yeah, so from 6th you can just go through the you should be able to like calculate the transform data points and all from in the PCA process, and you should be able to know regarding if you have been given some sort of function, you should be able to tell regarding the whether it's this function or this matrix is positive, definite or not, or you should be able to convert that matrices into what you can say into matrices into not matrices, function into matrices, right?
Okay.
And what else was there? Yeah, this is all about the week 6th, right? So the concepts are very limited. You should be, yeah. So these are the, I guess, important concept you should focus on. PCA simple, and then with any matrices, you should be able to say regarding the whether it's a positive definite or semi-definite or negative, those sort of things. If there is a function has been given in the form like if the plot has been given, you should be able to calculate the stationary point. You should be able to tell whether this stationary point in minima and maxima, those sort of things, and that's it. So you won't face much problem in solving those questions.
Okay.
Yeah, and in week 8, mostly just focus on the properties. The question would be like to convert. The question would be converted. It's just that you will check that property whether you are observing that property in the mathematical form only. That's it. The like what is the property of convex set, convex function, and yeah, one question you can expect like this only, like just convert that function into the matrix form, that Hessian matrix form. Okay.
Okay.
Yeah.
And so one last I would like to ask, like for week 6, I went on break for some time in your lecture. So I wanted to know, like, so I can go and check the recordings on YouTube. But like, have you explained how we can write like 3 variable function in a matrix form, like x square plus 2xy plus y square plus 2xz
Yeah.
plus 2yz likewise.
Like after this week 8, I covered that. So yeah, like just 20 to 25 minutes back, it was covered.
Okay, sure.
Yeah, that is what I'm saying. Yeah,
Yeah,
that
you
is
can
what
just
I'm.
work. And the one more thing, in the exam with the MCQ, if the question came in form of MCQ, you can just go to it and like hit and trial can also work in that. Okay.
In minute.
Yeah. Yeah, we can multiply the matrices, and if
Yeah.
that matches to the equation, yeah, that is all.
Yeah.
But yeah, if but if that is not the question, if the question is at next level, right? Like you need to.
Okay, yeah, then you can do that. You can just clearly differentiate with respect to x, y, and then that Hessian matrix, right? And that we have to calculate the
So
Hessian
Hessian matrix, like that's what my question was earlier. So yeah, if that is explained, I can go back and check.
Yeah,
But
you
yeah,
can just go through and you can watch this.
yeah, sure, sir. Thank you so much.
Yeah. So okay then. Thank you everyone. And okay.
Yeah.
Thank you, all instructors. It was so informative and helpful session for us. Thank you very much.
Thank you for your effort.
Yeah,
Thank you, sir.
Yeah, thank you everyone. Okay, Jimmy, bye.
And sir,
Yeah.
when can we expect this document to be uploaded?
Okay, so we'll upload it after this session for sure. Okay.
Okay, last
Thank you,
you shared some image for the multiple matrix, I think, for multiple.
Yeah, that was covered. That was covered in week 8 as HWI. I think. Yeah, I had covered this.
Yeah, this is what this is the Hessian matrix. Okay.
Yeah, so I had covered one question because someone has asked me to cover that. So yeah, that's why I think, yeah.
Sure, sir. I'll check.
You can go through the slide also. This slide will also be shared.
Yeah, week 8 HWI session. There we had converted this this equation to that matrix format. Okay.
Okay. So where can I expect the slides?
Slide would be there, I think so. But yeah.
Where generally upload, Jimmy, the slides?
I think it would be in that supplementary folder only.
Okay, supplementary folder will tell them to upload.
Yeah, okay. And sir, the other material which you have explained in the revision session, like can we expect it to be uploaded by today?
Yeah. We'll upload all those things right now after this session.
Yeah, sure. So that would be really helpful.
Okay.
Yeah. Thank you so much, sir, for all your efforts. Thank you, everyone.
Thank you, sir.
Okay, thank you.
Yeah, all the best for the quiz.
Thank you.
Okay, then I'll tell them to close the session. Okay, bye Jimmy, bye Ram.
Yeah. Bye Ram. Bye.